Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. The world outside may rush and clamor, filled with 1,000 demands and the relentless tick-tock of urgent moments. But here, in this quiet corner, we've carved out together, we can allow those pressures to simply dissipate like mist, vanishing in the warmth of a gentle morning sun. Let your shoulders relax. Feel the soft support beneath you and allow your breath to deepen, slowing its rhythm until it mirrors the tranquil ebb and flow of the ocean at dusk. This is a sanctuary for thought, a quiet harbor where the winds of everyday concerns cease to stir and our minds are free to drift unburdened across the vast and mysterious waters of the cosmos. As the last lingering blush of daylight fades from the horizon, giving way to the velvet indigo of twilight, and the first hesitant stars begin to prickle through the darkening canopy, casting their ancient silent vigil upon our world. Our minds, too, can embark on journeys, not physical journeys across continents or oceans, but expeditions into the realms of pure imagination and gentle inquiry. Tonight, we're going to tiptoe into one of the most profound and perhaps one of the most mysterious questions ever asked by humanity. It's a question that stretches the very fabric of our understanding, inviting us to ponder realities far removed from our daily experience. How we might softly ask ourselves, would our universe, this vast, intricate tapestry, woven from starlight and silence, from galaxies wheeling in grand cosmic dances, and from the delicate shimmer of distant nebulae, fundamentally change if we could even for a fleeting, improbable moment approach the very speed of light? What secrets would space, that seemingly empty expanse, begin to whisper to us? And how would time, that relentless river which carries us all forward, reshape itself around our fleeting presence, bending and flowing in ways we can barely conceive? This isn't a brisk sprint through complex equations, nor is it a rigorous lecture meant to challenge your waking logic with dizzying paradoxes. Instead, think of it as a quiet, contemplative stroll through a cosmic garden where each idea we encounter is a rare and exquisite bloom. We will simply pause to admire its beauty, its intricate patterns, and its subtle, often bewildering fragrances. We'll touch upon concepts that often feel abstract and distant, like faint echoes from another dimension or the soft rustle of leaves in an unseen forest. But we'll do so with the gentlest of hands, transforming these profound notions into images and feelings that resonate with our everyday experience, even as they stretch the very fabric of our understanding to its beautiful, elastic limits. Imagine, if you will, sipping a warm cup of chamomile tea, its comforting steam rising in gentle swirling spirals into the hushed air as we float effortlessly through a galaxy of ideas. We will allow the currents of thought to carry us wherever they may lead, unburdened by the need for definitive answers or the pressure to grasp every nuance. For tonight, the true beauty lies not in solving the mysteries, in definitively labeling every star, but in embracing them, in allowing ourselves the boundless luxury of pure, unadulterated wonder. We're here to feel the quiet weight of these grand cosmic concepts, to sense the extraordinary, almost balletic dance of space and time, and to simply be present with the marvels that lie just beyond our ordinary earthbound perception. So close your eyes if you wish. Let your breath slow and allow your imagination to take flight, gently, silently into the heart of the cosmic unknown. The universe, in its incomprehensible vastness, holds secrets that seem to whisper to us from the farthest reaches of every star-dusted night. We tiny sentient beings stand on a minuscule blue dot, gazing up at the glittering expanse, above an instinctual longing stirring within us. We wonder, what if? What if we could somehow break free from the familiar constraints of our everyday existence, from the gentle, ever-present pull of Earth's gravity which keeps our feet firmly planted, from the steady, comforting tick-tock of our clocks, which measures out our lives in predictable seconds, minutes, and hours? What if we could truly accelerate, not just with the brute force of a rocket, but with a grace that transforms our very being. What if we could feel the authentic, unadulterated wind of the cosmos on our faces, not merely as a poetic metaphor, but as the very fabric of space-time, bending and rippling around our fleeting presence? This is not simply a whimsical flight of fancy. It's a deep-seated ancient human desire to push the boundaries of what is known, to see beyond the translucent veil of the ordinary, to touch the edges of the impossible. And in the profound quietude of this moment, as the day finally releases its tenacious grip and the night unfurls its vast, silent velvet cloak across the sky, we allow ourselves the privilege to explore these profound possibilities, not with the frenetic urgency of a scientific expedition racing against time, but with the meditative calm and gentle introspection of a dreamer drifting on the edge of sleep. Consider the very notion of speed itself. In our terrestrial lives, we measure it in familiar terms, miles per hour or kilometers per hour. We experience it as a tangible, visceral sense of movement, a blur outside the car window, the exhilarating rush of a train, the silent ascent of a plane soaring through the clouds, the thunderous roar of a rocket blasting off into the inky blackness of orbit. Each of these represents an incremental increase in velocity, a pushing against the constant invisible resistance of air and the enduring pull of gravity. But the speed we are contemplating tonight is of an entirely different order, an altogether different magnitude. It is the cosmic speed limit, the ultimate insurmountable barrier, a radiant beacon that calls to us from the very deepest foundations of reality. It is the speed of light, an almost unimaginably swift velocity, a breathtaking constant that shapes and defines everything we perceive, everything that is, yet it remains tantalizingly just beyond our physical grasp. What would it truly mean, not just intellectually in the cold light of theoretical physics, but on a deeply experiential, even spiritual level, to approach such a fundamental universal limit? How would the world, in all its familiar forms and vibrant colors, transform before our very eyes? Would the trees still retain their comforting green? The sky its boundless blue? Would our own bodies, these delicate vessels of flesh and bone, feel the same? Or would they too undergo a profound, perhaps bewildering metamorphosis, shifting and changing in ways we can barely begin to fathom? Tonight we are not seeking definitive, absolute answers that can be neatly filed away. Rather, we are seeking a deeper, more profound understanding of the questions themselves. We are here to appreciate the inherent elegance of the universe's design, even in its most extreme, mind-bending manifestations. Imagine for a moment a smooth, perfectly calm lake, its undisturbed surface reflecting the soft, muted colors of the twilight sky above. Now gently, imagine a single pebble dropped into its absolute center. Ripples, concentric circles of disturbance, spread outwards, ever expanding, moving gracefully across the water's surface. This is a simple yet powerful analogy for how light travels, emanating from a source, expanding its silent influence across the vastness of space. But what if we, as conscious observers, could somehow race alongside those ripples, matching their incredible speed, or even drawing incredibly, improbably close to it? What then would the ripples look like? Would they still be recognizable as ripples, or would they flatten, solidify, become something utterly new, something indescribable, something that defies all our preconceived notions of form and motion? These are the kinds of gentle provocations we will explore, allowing our minds to stretch and adapt to new perspectives. Much like a supple, resilient branch, bending gracefully in a soft, persistent breeze, never breaking, only yielding to the unseen force. The profound beauty of these concepts lies not in their complexity, but in their ability to humble us, to remind us of the sheer, unfathomable vastness of what we do not yet know, and the astonishing, almost poetic precision of the laws that govern everything from the smallest, most elusive atom to the grandest, most majestic galaxy. It's a journey into the very heart of physics. Yes, but more importantly, it's a journey into the heart of pure, unadulterated wonder. Each new idea we encounter tonight will be like opening a new previously unnoticed window in a dimly lit room, allowing a sliver of distant starlight to illuminate a previously unseen, perhaps dusty corner of our understanding. We won't dwell on the intricate mathematical complexities that underpin these theories, but rather on their simple yet profoundly awe-inspiring implications. How time, that seemingly unwavering, immutable companion, can bend and stretch like a fabric pulled taut. How space, our familiar playground, the very stage upon which our lives unfold, can warp and ripple, defying its apparent solidity. These aren't just abstract equations scribbled on a blackboard in a distant university. They are the very foundational threads from which the universe in all its astonishing complexity and elegance is woven. And tonight, we are simply reaching out to touch them, to feel their extraordinary texture, to marvel at their intricate cosmic design, to whisper questions into their silent depths. So let any lingering thoughts of the day, any worries that might still cling to your mind, simply dissolve like delicate snowflakes melting upon warm glass. Allow yourself to settle deeper into your comfort, to become one with the stillness that surrounds you. The quiet hush of the approaching night. The world outside, with all its demands and distractions, can wait patiently until the dawn. For now, there is only this quiet exploration, this gentle unfolding revelation of cosmic secrets whispered softly into the receptive stillness of the night. We are embarking on a voyage not of physical distance, measured in light years or parsecs, but of conceptual depth, a journey that promises not to exhaust your mind, but to enrich your spirit. Not to confuse you with technical jargon, but to inspire you with the boundless possibilities of the unknown. And as we drift through these profound, often paradoxical ideas, may you find a deeper, more settled sense of peace, a quiet, abiding appreciation for the sheer magnificent grandeur of the cosmos, and perhaps a renewed sense of the silent, pervasive magic that permeates every hidden corner of our existence, waiting patiently to be discovered. Welcome once again to this tranquil space, this sanctuary of thought, where the universe reveals its wonders, one gentle contemplative thought at a time. May your journey be serene and your dreams be filled with starlight. Tonight, we gently approach a fundamental truth, a cosmic speed limit woven into the very fabric of existence, a boundary that silently dictates what is and what is not possible in our grand universe. For all our striving, our engineering marvels, and our boundless curiosity, there is a threshold, a luminous barrier, that material objects like you and me can never truly cross the speed of light. This isn't just a matter of building a faster engine or designing a more aerodynamic spacecraft. It is a deep intrinsic property of reality itself. Imagine, if you will, standing at the edge of a vast, shimmering ocean. You can wade and swim vigorously, even ride the fastest boat across its surface, but you can never become the wave itself, moving at the wave's own inherent speed across the water. You are separate. You are limited by your own nature as a body interacting with the medium. In a similar yet infinitely more profound way, we as beings composed of matter are bound by the universal speed limit of light. The reason for this ultimate barrier lies in a concept that at first whisper might seem counterintuitive: the relentless, ever-increasing demand for energy. To even begin to imagine accelerating something with mass, a starship, a pebble, or even a single atom, closer and closer to the speed of light, we must confront an extraordinary truth. The energy required does not simply increase steadily, like filling a bathtub. No, it grows exponentially, surging upward with a ferocious intensity. The closer you get to that luminous threshold, picture a colossal ancient mountain, its slopes gentle at first, inviting, and seemingly easy to ascend. You begin your climb, your steps steady, your energy expenditure manageable. But as you ascend higher, inching closer to the very summit, the incline suddenly steepens. Dramatically. Each step now demands exponentially more effort, more strength, more fuel from your very being. The air thins, the ground becomes treacherous, and the peak, though seemingly within reach, becomes an almost impossible, unattainable goal. This is the cosmic mountain we face when contemplating light speed. Every tiny fraction of a percent closer to that ultimate velocity requires an unimaginably greater input of energy than the fraction before it. It's as if the universe itself is creating an invisible, yet incredibly potent, resistive force, pushing back against any attempt to breach its most fundamental speed limit. To reach the speed of light would in essence demand an infinite supply of energy, a wellspring that simply does not exist within the finite confines of our universe, an infinite amount of push for a finite object. Yet in the grand cosmic ballet, there are fleeting, almost ghostly instances. Subtle whispers of matter coming incredibly tantalizingly close to this impossible dream. Scientists, with their keen instruments and patient observations, have witnessed some subatomic particles. Those tiny ephemeral dancers within the quantum realm traveling at velocities that beggar belief. We've observed particles, for instance, hurtling through colossal particle accelerators, or arriving from the distant reaches of space as cosmic rays at speeds reaching an astonishing percent of the speed of light. Imagine that. It's not just 99%, it's 99% with a string of nines trailing behind it like a shimmering, infinitely long tail. These are not grand starships, of course, but fundamental building blocks of reality itself. So tiny they are almost beyond our grasp. Yet they possess energies so immense, so concentrated, that they graze the very edge of this universal speed limit. Think of them as cosmic sprinters pushing their tiny, almost massless forms to the absolute brink of what the universe allows, leaving behind a faint, almost imperceptible wake that whispers of extraordinary possibilities. For us, embodied beings made of countless such particles, such speeds remain firmly within the realm of speculative fiction, a beautiful, impossible dream. Our existence, our very coherence, relies on the slower, more stable rhythms of a universe where light defines the ultimate pace. Now for you and me with our human scale, our soft skin and our steady heartbeats, there is no hope, none at all, of ever truly approaching these mind-bending speeds. Our bodies, our very consciousness are woven into a slower, gentler fabric of reality. The energy required to accelerate even a single fingernail to such a velocity would dwarf the entire energy output of our sun for millennia. It's a humbling thought, isn't it? Yet the beauty of the mind, that boundless inner universe, is that we can imagine it. We can play the what-if game, allowing our thoughts to dance on the edge of the impossible. So let us indulge in this gentle thought experiment. If by some miraculous, impossible cosmic twist of fate, you did manage to approach these speeds, to feel the universe whizzing by in an unfamiliar blur, what would truly happen? What would the world around you look like? How would space itself, that familiar expanse we navigate daily, contort and twist? And how would time, that steadfast companion, that constant, relentless arrow of our lives, begin to act? From your perspective, that of the intrepid, accelerating traveler, the changes would be profoundly noticeable, deeply visceral, and utterly unlike anything you are currently used to. It would be a symphony of distortions, a ballet of warped realities, playing out just for you. Let's ease into this gently, as it's going to be a bit tricky to truly wrap our earthbound heads around these concepts. Our minds are wired for the slow, predictable rhythms of everyday life where things move at speeds we can easily comprehend. But the universe, in its grand design, holds far more intricate dances. We will simulate this extraordinary journey, moving from a comfortable standstill, perhaps just standing quietly in a field, to traveling almost at the speed of light. This isn't a mere abstract calculation. We can draw inspiration from a rather fun and insightful little game, a beautiful thought experiment brought to life called A Slower Speed of Light. This game, developed by brilliant minds at MIT, was designed to demonstrate in a wonderfully intuitive way What would happen if the speed of light itself progressively slowed down, eventually descending to a pace as familiar and unthreatening as a leisurely walking speed? It's a clever inversion, isn't it? Instead of us speeding up to match light, the game slows light down to meet our familiar human pace. It allows us to step into a world where the strange effects of relativity are not just theoretical whispers, but tangible, visible phenomena. At first, in this imagined journey, as our character, or perhaps simply our mind's eye looks around the world, appears perfectly normal, utterly familiar. The trees are green, the sky is blue. The distant mountains retain their familiar contours. There's no hint of the cosmic ballet about to unfold. But then, as we begin to interact with this simulated environment, perhaps by collecting shimmering orbs that float in the air, a peculiar transformation begins. Instead of these orbs accelerating us, which would be our natural expectation, the game with its brilliant design slows the very speed of light itself down. It's a masterful stroke, allowing us to vividly simulate what the universe would look like, what it would feel like if we were the ones traveling at an extremely rapid pace across immense, sprawling distances. The familiar, unwavering constant of light begins to yield, becoming more pliable, more responsive to the speed of our interaction. As the speed of light, this fundamental constant, begins to slow its cosmic dance within this simulated world, what becomes strikingly, almost uncomfortably apparent to our senses. The very first thing, the most immediate and startling sensation that begins to wash over us, is that the colors of everything around us start to change. The familiar palette of our world begins to shift, to bleed into new, unfamiliar hues, like a painter's canvas undergoing a subtle yet profound transformation. This isn't an optical illusion caused by tired eyes or a trick of the light in the common sense. No, this is due to a deeply fundamental phenomenon known as the relativistic Doppler effect. You see, when you look around right now in your own comfortable space, and you perceive the vibrant colors on objects, the deep green of a leaf, the vibrant red of a flower, the soothing blue of the sky, this is because light in its essence is reaching your eyes at very specific, precisely defined wavelengths. Imagine light not just as a continuous glow, but as tiny invisible waves, like ripples on a pond, each with its own unique length. The longest of these wavelengths that our human eyes are capable of detecting, of truly perceiving, appear to us as the warm, comforting shades of red. Conversely, the shortest, most tightly packed wavelengths register in our consciousness as the cool, ethereal hues of violet. Beyond the immediate visible range of our limited human sight lie other fascinating realms. The long, unseen waves of infrared, which we often perceive as heat, and the short, equally invisible waves of ultraviolet, which can cause a fluorescent substance to glow with an otherworldly light. These are all part of the vast electromagnetic spectrum, a grand cosmic symphony of light, most of which remains utterly hidden from our everyday perception. But now, as you begin to travel at an incredibly rapid pace, pushing against the very boundaries of conventional motion, something extraordinary happens to these light waves because of the Doppler effect, just as the pitch of a siren changes as an ambulance rushes past you, becoming higher as it approaches and lower as it recedes. So too do the wavelengths of light shift when you are moving at relativistic speeds. Imagine you are running very, very fast towards a source of light. As you race forward, you are essentially compressing the light waves in front of you, squishing them closer together. This compression causes their wavelengths to shorten. Conversely, as you speed away from a light source or look at light coming from behind you, you are stretching those waves, making their wavelengths longer. What does this mean for our perception of color? It means that some of the wavelengths that were previously in the long unseen realm of infrared now suddenly shift into the range that your eyes can detect appearing as a fiery red or a warm orange. And astonishingly, some of the wavelengths that were once in the short hidden realm of ultraviolet now stretch and shift into the visible spectrum, revealing themselves as a brilliant, shimmering blue or vivid violet. Suddenly, things that were utterly invisible to us just moments before when we were standing still now become strikingly visible. Imagine being able to see the warmth radiating from a nearby object, not just feel it, but perceive its heat signature as a glowing pulsating color, like an aura made of pure warmth. Or picture fluorescent substances, which normally only glow under special ultraviolet lights, now shimmering and vibrating with their own inherent luminescence, simply because you are moving. The faster you travel, the more pronounced this effect becomes. It's as if your entire visible range, the very window through which you perceive the universe, begins to expand, stretching its boundaries, revealing layers of reality that were previously hidden. Your eyes, once limited to a narrow band of the electromagnetic spectrum, become instruments of extraordinary perception, pulling in new colors, new forms of light from the unseen depths of the universe. It's like gaining a new sense, an entirely new way of experiencing the world, where the subtle energies that underpin existence suddenly burst forth in a riot of unexpected hues. This isn't just a shift in existing colors. It's an unveiling, a grand revelation of light that was always there dancing around us, but remained stubbornly beyond our grasp until our speed unlocked its hidden beauty. The familiar world around you transforms into a vibrant, shifting canvas, a dynamic interplay of light and energy that pulses and changes with your every increase in velocity, reminding us that reality, far from being static, is a fluid, responsive symphony constantly waiting to surprise and astonish us. We've just begun to glimpse the astonishing transformation of color, that vibrant tapestry woven from light's very essence. But light, as we know, is a profound enigma, a cosmic chameleon. While it undeniably travels in waves painting our world with its myriad hues, it also arrives as a relentless stream of tiny invisible particles known as photons. Imagine, if you will, standing in a gentle, persistent rain. Each droplet is distinct, a tiny individual entity. But when countless droplets fall together, they form a continuous sheet of water, a wave moving across the ground. Photons behave in a similar wondrous duality. They are individual packets of light racing through the cosmos, yet their collective movement creates the undulating flow we recognize as a wave. Now picture yourself not just moving, but truly hurtling forward, accelerating to speeds that defy our everyday understanding, heading directly into this ceaseless flow of light particles. As you surge forward, you are in essence running headlong into the very current of these photons. What happens then? The answer is beautifully, strikingly simple. The more particles will hit your eye. It's like charging into a blizzard, where every step forward brings a greater density of snowflakes pelting against your face. Or imagine a swimmer bravely pushing against a powerful river current. The water hits them with greater force and frequency than if they were simply floating downstream. In the same way, as you speed towards the sources of light, you are increasing the rate at which photons impact your retinas. This intensified bombardment of light particles means that everything ahead of you will become strikingly, overwhelmingly brighter. The world in front of you transforms into a dazzling, almost blinding crescendo of light, a searchlight beam pointed directly from the universe into your very being. Details might merge into an incandescent glow. Familiar shapes might dissolve into brilliant halos as the sheer volume of light overwhelms your senses. It's a spectacular, almost terrifying illumination, a direct consequence of your headlong rush into the cosmic river of photons. On the other hand, if you were to cast your gaze behind you, as you continue to travel relentlessly forward, away from the sources of light you've already passed, a stark contrast emerges. The landscape you've left behind, the shimmering trail of your journey, will begin to grow noticeably steadily darker. Why this sudden dimming? Because as you accelerate away, you are essentially outrunning the photons that are trying to reach you from behind. Imagine leaving a room and trying to see the light emanating from a lamp you've just passed. If you're walking away at a normal pace, the light still catches up to you, though perhaps a little less intensely. But if you're sprinting away at incredible speeds, the light waves trying to follow you struggle to keep pace. Fewer and fewer photons from those distant receding sources manage to catch up and strike your eyes. It's like sailing swiftly away from a lighthouse. The further and faster you move, the fainter and more elusive its beam becomes until it finally fades into the encompassing darkness. This phenomenon, the intense brightening ahead and the profound darkening behind, is so striking, so dramatic, that it has earned its own evocative name, the searchlight effect. Your very presence, your extraordinary speed transforms you into a living, moving beacon, casting the path ahead in an almost unbearable brilliance, while simultaneously plunging the world you've left behind into a growing, impenetrable shadow. It's a stark, undeniable visual testament to the profound forces at play when you dare to approach the universe's ultimate speed limit. As these astonishing changes in color and brightness wash over you, one might begin to notice another peculiar sensation, something that subtly reshapes your very perception of motion. You might distinctly feel that you seem to be gradually speeding up, as if an unseen force is continuously propelling you faster and faster into the cosmic unknown. There's a persistent, almost exhilarating sense of acceleration, a building momentum, that suggests you are breaking free from all earthly constraints. Yet here lies one of the most remarkable and counterintuitive truths of this extraordinary journey in our simulated game, our actual walking speed. Our intrinsic pace always stays the same throughout the entire experience. From the very first step, when we were simply walking at our normal, familiar rhythm, to the moments when the universe begins to distort and warp around us, our physical speed, our rate of traversing the ground beneath our feet remains constant. It's like being on a treadmill, set to a fixed pace, yet somehow the world around you seems to rush by with increasing urgency. This profound illusion of accelerating, this deceptive sensation of a building crescendo of speed, is a direct and elegant result of special relativity, one of the deepest and most beautiful insights into the fundamental workings of our universe. Specifically, it is a manifestation of time dilation, a concept that once grasped reshapes our very understanding of time itself. One of the unwavering ironclad laws of the universe, a cornerstone upon which the entire cosmos is built, is that the speed of light is an absolute constant. No matter how fast you are moving or in what direction, if you measure the speed of a beam of light, it will always be precisely the same, an unyielding, universal benchmark. It's like the universe has a perfectly calibrated cosmic odometer for light, and it never ever wavers. However, and this is where the mystery deepens and the wonder truly begins, space and time are not constant. Far from being rigid, unchanging backdrops against which the drama of the universe unfolds, they are pliable, dynamic entities that can be warped, stretched, and compressed. They are like a vast, invisible cosmic fabric, capable of bending and curving in response to energy and motion. So when you, a tiny piece of this cosmic fabric, begin to move at extraordinary speeds, two fundamental aspects of your reality undergo a profound transformation, subtly reshaping themselves. Relative to stationary observers, those who remain rooted in a slower, more familiar reality, watching your incredible journey from afar. Those two aspects are your time and your distances. Let me explain this gently, as it's a concept that truly challenges our ingrained perceptions. The universe, in its elegant wisdom, has a remarkable way of preserving that constant speed of light. To do so, it allows time itself to become flexible. For an object that goes faster, time from the perspective of an outside observer literally goes slower. It's as if time, that relentless river, suddenly becomes sluggish, its currents losing their familiar urgency, flowing with a deliberate, almost dreamy slowness. This isn't mere theory. It's a phenomenon that has been proven meticulously and repeatedly by precise scientific experiments. Imagine, if you will, two identical, perfectly synchronized clocks. One clock remains stationary, resting peacefully on a tabletop, ticking away its seconds in a familiar steady rhythm. The other clock, however, is placed in rapid continuous motion, perhaps aboard a cutting-edge rocket, circling our planet at incredible speeds for an extended period. When that rocket eventually returns and the two clocks are brought together again, an astonishing truth is revealed. The times displayed on each clock will be subtly, yet undeniably, out of sync. The clock that experienced rapid motion will have recorded less time than its stationary counterpart. Its journey through time has been slightly infinitesimally slowed down. This isn't just a fascinating laboratory curiosity. It has profound, real-world implications that highlight the constant subtle dance of time dilation in our own solar system. This is precisely why the ultra-precise clocks aboard the satellites in orbit around Earth, which are crucial for technologies like our GPS navigation systems, need to be occasionally adjusted. If these adjustments weren't made, their internal clocks, subtly affected by their rapid motion through space and their slightly different gravitational environment, would gradually go out of sync with the Earth-based clocks. The discrepancy might not seem like much at first, perhaps just a few milliseconds per year. A mere blink of an eye, hardly noticeable to our casual human senses. But over time, these tiny accumulated differences would add up, growing into significant errors that would render our GPS systems and countless other precise technologies utterly useless. It's a silent, constant testament to the universe's elegant bending of time playing out above our very heads, every single second. The implications are clear. The faster you go, the more time dilation happens. The slowing of time becomes increasingly pronounced, more significant, more tangible as your velocity inches ever closer to that ultimate cosmic speed limit. Imagine that the rate of time for you is a gentle flowing stream. As you accelerate, that stream begins to broaden, to deepen its currents, becoming more languid, more reluctant to move forward. Until, should you by some impossible feat actually hit the speed of light, the rate of time for you would theoretically reach absolute zero. It would simply cease to flow. This means that for photons or light particles, which inherently travel at the speed of light, they are in a profound and almost mystical sense unaffected by the passage of time. From their perspective, their journey from the distant heart of a star to your eye, a journey that might span billions of our earthly years and unimaginable distances, happens instantaneously. For a photon, there is no before or after, no past or future. There is only now, an eternal, a luminous present. They are truly timeless travelers, cosmic immortals gliding through an eternity that is to them but a single, endless moment. But let's gently guide our thoughts back to how this extraordinary concept of time dilation affects us in our simpler simulated journey. To truly grasp its subtle dance, let's imagine momentarily removing those vivid lighting effects we discussed earlier. With the riot of shifting colors and blinding brightness set aside, we can see this effect a lot more clearly, allowing its quiet strangeness to truly settle in our minds. Remember, throughout our game, our basic walking speed, our internal sense of pace, our legs moving at a consistent rhythm, stays perfectly the same. It's the universe around us, or rather the simulated speed of light within it, that slows down as we collect more and more shimmering orbs. And yet, despite our unchanging physical effort, it seems unequivocally that we move a lot faster towards the end of the game than we did at the beginning. The world rushes by with an increased urgency, distances melt away with a peculiar swiftness, and there's an undeniable sensation of picking up incredible accelerating speed. What then is truly happening here? It is the beautiful mind-bending consequence of time dilation. Our time is going slower than everything around us. While we continue to experience seconds and minutes at our normal internal rate, the external universe, for those observing us from a stationary frame, is experiencing time at its usual faster pace. It's as if your personal clock has subtly, imperceptibly begun to lag behind the cosmic clock. As a direct result of this intimate personal slowing of time, a remarkable spatial distortion occurs from your perspective. It's like the distances of space themselves are becoming shorter. The vast stretches between objects, the familiar miles and kilometers, seem to shrink to compress like a great cosmic accordion, gently squeezing itself. This means that from your unique, time-dilated perspective, we get somewhere quicker. The journey feels swifter. The destination appears to rush towards us with a startling immediacy, not because we are accelerating in the conventional sense, but because the very fabric of space and time has rearranged itself around us, bending to accommodate the universe's unwavering commitment to the constant speed of light. In practical terms, in the grand hypothetical theater of the cosmos, this means something truly profound. Imagine for a moment that we could travel in a vehicle, a magnificent starship, that actually approaches the unfathomable speed of light. If we were to travel for, say, 1 Earth year at that incredible speed, for us aboard that vessel, the passage of time would feel completely normal. Our hearts would beat at their usual rhythm, our meals would pass, our days would turn into weeks, and weeks into months, just as they always do. We would age perhaps by 1 year. But the astonishing truth, the mind-bending reality, is that for people remaining on Earth, rooted in their slower, more familiar frame of reference, 10 years or even hundreds or thousands of years might have passed. You would return to a world utterly transformed, a future that for you is still distant, but for them has long since unfolded. It's the ultimate journey into the future, a one-way trip through the river of time, a bittersweet testament to the universe's extraordinary flexibility. Should you actually impossibly be able to truly travel at the speed of light, not just approach it, but reach it, the implications are even more staggering. From your unique timeless perspective, you could traverse the entire universe from one end to the other to the farthest galaxy instantaneously. The journey would take no time at all for you. It would be a single, eternal now. But for people back on Earth, the amount of time that passes would be precisely equal to the distance you've traveled in light years. So if you desired to venture 40 light years away from Earth to a distant star system, and you could miraculously travel at the speed of light, you would arrive there instantaneously from your personal perspective. Yet for the people patiently waiting on Earth for your loved ones, for humanity itself, you would show up there 40 years later. Your arrival would be a ripple across their future, a historical event unfolding decades after your departure. It's a profound, almost melancholic thought that while you experience timeless ubiquity, the universe around you continues its relentless march through the ages. Again, though, and this is the gentle but firm hand of reality reminding us of its boundaries in practice, lightspeed travel is truly impossible for anything made of matter. Our dreams of instantaneous cosmic journeys of returning to a vastly changed Earth must remain for now within the beautiful, boundless realm of imagination. The universe has set its rules, and for matter, the speed of light is not a destination, but a tantalizing, unreachable horizon. It's a whisper of possibility, a beautiful thought experiment, but not a pathway for our embodied selves. Yet the very act of contemplating it, of allowing our minds to stretch to these impossible limits, illuminates the subtle, profound ways in which time and space are woven, not as static, unchanging backdrops, but as fluid, responsive elements of a deeply interconnected cosmos. As we continue our imaginary journey, gracefully nearing the ultimate speed limit of the universe, the last effect we might begin to notice is perhaps the most disorienting, the most profoundly strange of all. It's as if our very field of view changes not just in how bright things appear or what colors we perceive, but in the fundamental way we see the world wrapping around us in an almost alien fashion. This peculiar visual distortion stems from the combined effects of something called the aberration of light and the mathematical elegance of the Lorentz transformation. Two concepts that dance together to reshape our visual reality at extreme velocities. Let's gently unpack this. At its core, the reason for this strange shift in our vision lies in a simple yet profound truth. that we rarely consider in our everyday lives. Light takes time to reach our eyes. Even now, as you softly listen to these words, perhaps gazing at a screen or into the quiet stillness of your room, you are not truly seeing the present moment. The light leaving your screen or reflecting off the objects around you takes a tiny, infinitesimally small fraction of a second to travel across the distance to your eyes. So what you are perceiving is always a glimpse into the past. It's an incredibly tiny delay, of course, measured in nanoseconds, so imperceptible that our brains seamlessly stitch it into what feels like a continuous real-time experience. But the truth remains, we are perpetual observers of a micropast. Now imagine our journey moving at an almost unfathomable speed through our simulated world. As we hurtle forward, that very slight time delay becomes profoundly significant. The object we are seeing, that tree, that distant mountain, that shimmering orb, isn't where we think it is anymore. Because light travels at a finite speed, the photons that left the object to reach our eyes departed from a specific point in space before we arrived there or before the object itself moved. By the time those photons finally reach our retinas, we or the object or both have shifted positions. It's like trying to catch a ball that was thrown from a moving vehicle you don't aim for, where it was when it left the thrower's hand, but where it will be when you try to catch it. Except here, it's our perception that's playing catch-up, always seeing a delayed, slightly misaligned version of reality. You might have watched the earlier parts of this simulated journey and thought to yourself, goodness, this traveler must be utterly useless at computer games. They keep crashing into walls, missing those valuable orbs. And indeed, from an outside perspective, it might seem that way. But this peculiar effect, this silent warping of visual reality, explains the apparent clumsiness. Because of the aberration of light, I'm not truly standing where I think I am relative to the objects I'm trying to interact with. The more orbs I collect, the slower the speed of light becomes in our simulation, and the more pronounced this visual lag. Consequently, to actually navigate effectively, to avoid those phantom walls, and successfully collect the orbs, I need to start turning and adjusting my movements a little ahead of what I'm used to. My instincts, honed in a world where light feels instantaneous, are suddenly rendered obsolete. It's like playing a video game with severe lag where your inputs are delayed and the world on screen doesn't quite reflect your real-time actions. This disjunction between perception and reality makes simple navigation an incredibly difficult, almost alien experience. It forces a complete rewiring of our spatial awareness, a challenge that truly highlights the deep connection between light speed and our perception of where we are. But this profound effect of aberration holds another almost magical consequence. It also means that paradoxically, I can see much more of my surroundings in one go. My field of view, the panoramic sweep of my vision, seems to expand dramatically, stretching out to encompass areas that would normally be behind me or far off to the sides. To understand why this might be, let's turn to a helpful animation, a visual whisper that illustrates this complex dance. Imagine a single point of light, like a tiny star. As I move forward at an incredibly high speed, the light source is constantly moving relative to me. The photons emitted from that light source travel outwards in all directions. Normally, from a stationary position, I would only see the photons that travel directly into my eyes from the front. But when I'm moving very, very fast, the photons that were emitted from the sides, or even slightly behind the light source, are now swept up by my forward motion catching up to my eyes. It's like running through a rain shower where the rain is coming straight down. If you stand still, the rain hits the top of your head. But if you run forward, the rain also hits your face, your chest, and even parts of your arms that were previously untouched. You're effectively running into rain that was originally falling beside or even slightly behind you. Similarly, as I hurtle forward, the light beams that were previously propagating outwards at angles that would not have entered my eyes if I were stationary are now, due to my immense speed, bent into my line of sight. Because the beam of light takes time to reach me, I am seeing where it was relative to me in the past, and my movement has effectively caught up to light that was previously aimed elsewhere. This means that when there is a rich tapestry of things to see around me, a landscape filled with objects and textures, it's as if my field of view increases exponentially, dramatically expanding as the very fabric of light itself wraps around me. I'm suddenly perceiving all these objects as they were relative to me in the past, and my high speed allows me to gather light from a much wider angle than would be possible at rest. It's like gaining peripheral vision that extends almost to my back, a nearly 360-degree awareness of my surroundings, but one that is fundamentally rooted in the delayed echoes of light. My vision becomes a grand, distorted panorama, stretching and bending the universe into a breathtaking yet unsettling embrace. Light, space, and time. These fundamental pillars of our reality become even more complicated, even more intertwined when we delve deeper into their relativistic dance. But for the purpose of our gentle journey tonight, I won't delve into the more intricate, mind-bending layers of these phenomena. Suffice it to say, the universe holds depths of complexity that continue to challenge even the brightest minds. All I can say for now, as we gently drift through these concepts, is that I am profoundly, quietly glad that light appears almost instantaneous for us in our everyday lives. That tiny, imperceptible time delay allows our world to feel coherent, stable, and predictable. Without it, our every step, our every glance would be a constant struggle against a fluid, ever-shifting reality, a dizzying ballet of perception and misdirection. This game, a slower speed of light, and our journey through its simulated world was a beautiful, elegant thought experiment. It allowed us to peek behind the curtain of ordinary perception, to truly visualize, to feel what the world would be like if light, that swift messenger of the cosmos, decided to slow its tireless pace. But even this ingenious simulation only scratches the surface of the truly problematic scenarios that relativistic effects would unleash upon our familiar world. It hasn't even begun to explore the profound, intricate consequences. If, for instance, our Earth, currently hurtling around the Sun at its astounding, yet relatively sedate orbital speed, were to suddenly approach relativistic velocities, how would the very structure of our planet cope? How would all our intricate electronic systems, our delicate technology, and the subtle dance of atomic bonds within matter be affected? These are questions that open up cascades of further mysteries, major issues that would redefine every aspect of our existence. Yet, in the opposite vein, contemplating these extraordinary effects also opens up tantalizing possibilities. The ability for us, or rather for technology we might one day devise to approach the speed of light, would be utterly beneficial for traveling truly large distances in incredibly short times. Imagine a journey to a distant star system, one that normally takes thousands of years, collapsing into mere months or even weeks from the perspective of the traveler. The vast, cold emptiness between galaxies, that seemingly insurmountable barrier to interstellar exploration, would suddenly shrink, become traversable within a single lifetime. This is the dream that fuels countless works of science fiction, the silent hope that one day humanity might reach out and touch the stars. However, and this is the bittersweet echo of time dilation, this incredible advantage for the traveler comes with a profound, almost heartbreaking cosmic cost. While you, the intrepid voyager, experience a compressed journey, perhaps returning from a distant star within what feels like a few short years of your lifetime is passing normally for the people remaining on Earth. The cosmic clock on your home planet continues its steady, relentless tick. This means that traveling anywhere in the universe and eventually coming back again could indeed be possible for you, the individual allowing you to witness the grandeur of distant nebulae and alien suns. But upon your return after your personal journey of a few short years, Earth would look a lot different. Decades, centuries, millennia, or even more might have passed, depending on how far you ventured on your profound cosmic journey. Your friends, your family, your entire civilization as you knew it would be long gone, replaced by generations untold. By a future that unfolded while you were merely traveling through what felt like a blink of an eye, due to the various relativistic effects beyond the confines of your accelerating ship. Everything would appear profoundly warped, the very stars themselves. The familiar constellations would twist and contort into unfamiliar patterns like reflections in a funhouse mirror. Your field of view would be greater wrapping around you in that strange, all-encompassing panorama we discussed. A significantly greater range of light wavelengths would become visible, painting the cosmos in hues and energies you never knew. Existed a symphony of unseen colors finely revealed, and directly in front of you, the world would be much, much brighter. An incandescent, almost blinding blaze of incoming photons. A cosmic searchlight illuminating your path forward. So there we have it, a gentle glimpse into how your universe would profoundly change if you were to approach the speed of light. It's a universe of fluid time, elastic space, and light that plays tricks on your perception, a testament to the astonishing and often counterintuitive nature of reality itself. It's a humbling reminder that our everyday experiences are but a tiny limited sliver of the full cosmic truth, and that beyond the veil of the familiar lies a world of unimaginable wonders waiting for our quiet contemplation. We've journeyed together through the captivating, almost dreamlike transformations that occur when we imagine approaching the speed of light. Now let's gently shift our focus, turning our gaze from the effects of extraordinary velocity to another equally profound, cosmic architect, gravity. For just as speed can stretch and compress the very fabric of time and space, so too can the invisible yet immensely powerful pull of massive objects. To begin to unravel this next layer of cosmic mystery, we must first address a fundamental question, one that perhaps doesn't cross our minds in the hustle and bustle of daily life. What exactly is time? This question, simple in its phrasing, has puzzled philosophers and scientists for millennia. It slips through our fingers like fine sand, impossible to grasp, yet undeniable in its influence. The celebrated American writer Mark Twain once wryly observed that time is what keeps everything from happening all at once. It's a beautifully concise way to capture its essence, isn't it? Time acts as the great separator, the invisible hand that meticulously arranges the events of our universe. It separates the laughter of yesterday from the quiet contemplation of today, and today's fleeting moments from the unfolding possibilities of tomorrow. Without time, all existence would be a single overwhelming chaotic instant. Every birth, every death, every sunrise, every whispered secret occurring simultaneously in an unimaginable cacophony. As you sit here in this peaceful moment, listening to these words, you are not doing what you were doing yesterday, nor what you will be doing tomorrow. You are in this very instant experiencing this moment, the unique, unrepeatable present. You are, whether you consciously perceive it or not, constantly traveling through time. And perhaps, surprisingly, you are doing so at a very specific rate, the normal steady speed of 1 second per second. This is the universal rhythm, the default pace shared by you, by me, and by everyone else on our tiny blue planet. It's the constant gentle flow of the river of time that carries us all forward inexorably in the direction of the future. We feel its passage in the aging of our bodies, the changing seasons, the growth of a child, the silent turning of the pages of our lives. This relentless forward motion, this steady progression, feels like the most constant, unyielding aspect of our reality. But this seemingly immutable speed, this relentless rhythm of 1 second per second, doesn't necessarily have to be the case. And this is where the extraordinary insights of Albert Einstein begin to gently unfold before us, revealing a universe far more flexible and astonishing than we might have ever imagined. Einstein, with his profound intuition, discovered that the faster we travel through space, the slower our own personal time becomes. It's as if time itself is capable of yielding, of softening its relentless pace to accommodate our spatial velocity. Imagine trying to row a small boat directly across a wide river. If you focus all your energy on rowing straight across, you move swiftly from one bank to the other. But if you also try to row vigorously downstream at the same time, maintaining your diagonal path, some of your forward motion across the river is converted into downstream motion, and it takes you longer to reach the opposite bank. In a profound cosmic echo of this, our journey through space affects our journey through time. This fascinating relationship between spatial motion and the flow of time continues all the way up to the very edge of the cosmic speed limit. Up until the point where if we somehow impossibly could travel at the speed of light, time would, from an external perspective, stop moving for us entirely. It would be a state of eternal now, a frozen instant, utterly timeless. For a photon, time holds no meaning. Its birth and absorption are simultaneous, regardless of the distance. If we were to embark on a hypothetical journey to an object, say a beautiful distant exoplanet, located 4 light-years away from us for the people patiently waiting here on Earth, watching our departure with their normal Earth-bound clocks, it would indeed appear that our journey took precisely 4 years to complete. They would track our progress, mark the passage of the seasons, and measure the aging of their world. But for us, the intrepid travelers aboard our lightspeed vessel, the perception would be utterly different. To us, we would arrive at our destination instantaneously, as if the vast cold expanse of 4 light-years had simply vanished, folded in upon itself, allowing us to traverse it in the blink of an eye. The universe would seem to have shrunk its distances, collapsing into nothingness. Although this sounds utterly incredible, like something plucked from the pages of the most imaginative science fiction, scientists have, with remarkable precision and ingenuity, proven that this actually happens. It's not just a theoretical musing. It's a verified aspect of our physical reality. One of the most elegant and compelling demonstrations involved 2 meticulously calibrated atomic clocks so precise they measure time down to the quantum hum of atoms. One of these atomic clocks was kept at a stationary location, perhaps nestled securely within a laboratory. The other, its identical twin, was placed on board a plane and flown around the world, circumnavigating our globe for an extended period, continuously increasing its speed relative to the Earth's surface. When the airborne clock eventually returned and was compared to its stationary counterpart, the results were unequivocal and astounding. The clock that had traveled faster, that had experienced the profound effects of motion, had actually recorded less time. It had aged ever so slightly less than the clock that remained still. This outcome was precisely in line with what Einstein's special relativity had so beautifully predicted decades earlier, a silent testament to the universe's elegant, time-bending choreography. So special relativity, with its astonishing insights into how motion affects time, is a very real phenomenon, a validated cornerstone of modern physics. But Einstein, with his towering intellect and profound intuition, didn't stop there. His later, even more encompassing theory, general relativity, predicted that this fundamental warping of time would also happen due to another ubiquitous cosmic force, gravity. Imagine gravity not just as a mysterious pull that keeps our feet on the ground, but as a colossal invisible indentation, a cosmic dimple in the very fabric of spacetime itself. Einstein predicted that the closer you are to a large source of gravity and the more mass that source of gravity possesses, meaning the deeper that cosmic dimple is, the slower time will go for you. It's as if time struggles to climb out of this gravitational well, its relentless flow impeded by the very presence of a massive object. This groundbreaking prediction was also meticulously proven to be correct, most famously in the Pound-Repka experiment in 1959. This ingenious experiment, conducted within the confines of a tall university building, involved shooting gamma rays, a form of high-energy light, from the top of the building down to the bottom. Scientists then precisely recorded whether anything had happened to the light waves as they traversed the vertical distance, moving deeper into Earth's gravitational field. What they found was a subtle yet undeniable shift. The frequency of the waves increased the closer they got to the Earth. Imagine cars on a congested highway. As they approach a traffic jam, they bunch up, the distance between them shrinking. Similarly, the peaks of the gamma radiation waves moved closer together as they descended, indicating a subtle increase in frequency. This seemingly minor shift was in fact undeniable proof that time slowed down ever so slightly for the gamma radiation as it moved closer to the Earth's gravitational pull. It was a whisper from the universe confirming Einstein's profound intuition. This effect, though incredibly subtle in Earth's relatively mild gravitational field, is significant enough that just like the effects of speed, our highly precise satellites have to be programmed to constantly account for it. When these satellites are further away from the Earth's gravitational influence, time actually moves infinitesimally more quickly for them compared to us on the surface. Without this constant delicate correction, their internal clocks ticking away at a slightly different rate would gradually go out of sync with our Earth-based clocks. This desynchronization would cause major problems for everything from GPS navigation to global communication networks, highlighting how even these minuscule distortions of time are crucial for the functioning of our modern world. And yes, you heard that, right? The Earth's gravity, that gentle pull that keeps us grounded, is indeed enough to cause time to slow down for us right here, right now, compared to someone floating far, far away in interstellar space. So you're probably thinking now with a renewed sense of curiosity, how much faster would time be going for me if I wasn't on Earth, or if Earth had no gravity at all? Well, and this is another gentle paradox of relativity. It's always a matter of perspective. The procession of time, the feeling of one second following another, will always appear the same from your perspective. You won't feel like you're going slower. You won't experience a dragging sensation in your own personal flow of moments. Your heart will beat at its familiar rhythm. Your thoughts will flow at their usual pace. Although you may, if you're sensitive enough, start to notice some truly weird stuff going on around you, as the external world seems to speed up or slow down in ways that defy your intuition. But it's the outside observer, the one watching you from a different gravitational field, or from a different state of motion, that has to deal with you, seeming to slow down or to speed up relative to their own clock. To truly find out an exact answer to this intriguing question, Einstein, in his profound genius, devised an elegant equation. We will gently explore this equation, not to solve complex mathematical problems, but to appreciate its silent beauty and the profound truths it reveals. It might look a little daunting at first, a series of symbols dancing on the page, but I promise you, it's not as fearsome as it appears. So to find out precisely how much slower time goes on Earth, compared to somewhere where there was absolutely no gravity floating in the cosmic void, all we need to know are a few key figures: how much mass the Earth possesses, how far we are from its very center, and then we can decide how much time we want to compare. Just to ease ourselves into this beautiful calculation, let's imagine we want to compare 60 seconds. If 60 seconds passes in our hypothetical place, unaffected by gravity, how much time passes for us here on Earth? When we plug in the astonishing figures, Earth's immense mass, our average distance from its core, and perform the gentle dance of the numbers, we arrive at our profound result. For every 60 seconds that passes in a completely gravity-free zone, people here on Earth experience only 59.99999 seconds. Now take a moment to let that number settle in your mind. It's incredibly close to 60, isn't it? The difference is almost imperceptible. In other words, a staggering 6 billion seconds have to go by before we even begin to notice a difference of a mere 4 seconds. This subtle discrepancy, this tiny cosmic lag, happens roughly once every 190 years. So realistically, over the course of your entire lifetime, you'll only gain about 2 seconds because of the Earth's gravity compared to a hypothetical existence in a place with no gravity at all. It's a little underwhelming perhaps in its immediate impact, but incredibly profound in its implications. It tells us that time truly is a fluid dynamic entity, even if its ripples are incredibly gentle in our everyday experience. However, we here on Earth are not just affected by our planet's benevolent gravitational embrace. We are also under the profound overarching influence of the gravity of our magnificent sun, the giant star that warms our days and illuminates our nights. In terms of our equation, the sun's mass is vastly monumentally more significant than Earth's. So let's try this cosmic arithmetic again, this time by gently inputting the enormous mass of the sun and our average distance from its fiery heart into our elegant equation. This will give us a new figure, revealing how much time goes by for us on Earth for every 60 seconds of actual unburdened cosmic time. The new number is 59.99994 seconds. While this is still an incredibly small difference, it is a more significant number than what Earth's gravity alone contributes. It means that you are only seeing a difference of a single second once every 3 years or so. Or, to put it another way, about 24 seconds over the course of an average human lifetime. So the sun, with its immense gravitational pull, adds a more noticeable, though still minuscule tug on the fabric of our personal time. But now let's turn our attention to Mercury, the innermost planet, the tiny speedy world that orbits our sun in a dizzying ballet. Mercury is much closer to the sun than Earth is. Surely time is significantly altered there, twisted and bent by the sun's overwhelming presence compared to our more distant home. With such a massive object as the sun so close by, how much more does time slow down for us on Mercury? For a hypothetical traveler setting foot on its scorching surface, the equation is essentially the same as before, a constant companion on our journey of understanding. The only new number we need to gently plug in is the precisely measured distance between the sun and Mercury. And the answer to our final intriguing question of how much time passes on Mercury for every 60 seconds of cosmic time is a fascinating whisper, 59.99299D990 seconds. This means that a staggering 60 million seconds need to go by before there's even a single second's difference between Mercury's time and the unaffected cosmic time. This happens roughly once every 1.9 years, which when scaled up across an entire human lifetime equates to about 38 seconds of difference. It's only about 14 more seconds than on Earth, a subtle additional ripple in the flow of time. But again, and this is crucial to remember from your point of view, as a hypothetical resident of Mercury, you wouldn't feel like you're gaining those extra seconds. Your own personal time would continue to move perfectly normally for you. Instead, it would be the distant Earth that appears to be moving ever so slightly faster from your perspective. So if you were to point a powerful telescope towards Earth from Mercury, you would theoretically observe 14 more seconds of Earth's history unfold than you would if you were living there yourself. Given that Mercury is a fairly inhospitable world, a barren sun-blasted landscape, this tiny time-bending advantage is probably not worth the immense effort of relocating there. So to summarize this delicate dance of time and gravity, does Mercury's extreme proximity to the sun allow time to move slower for you compared to Earth? Yes, it does, but only by a difference of about 14 seconds over your entire lifetime. In reality, time dilation due to gravity is not actually that significant, at least not in our own familiar solar system. The sheer mass of our sun, while immense to us, is simply not enough to truly stretch and distort time to any profoundly noticeable degree for us, even if we were as close to it as the tiny planet Mercury. Our sun would need to be literally millions of times more massive before we would begin to experience time dilation to any truly significant, life-altering degree. It's a humbling thought, a reminder of the scale of the cosmos. However, even though the practical effects in our neighborhood are subtle, it is still a truly fascinating insight into the intricate, often counterintuitive way that time flows in our universe. It gently reveals that time is not as constant, as rigid, as unwavering as we might instinctively think. It is instead a dynamic, pliable element, subtly shaped by the presence of mass and energy a testament to the elegant, responsive nature of reality itself. And of course, this profound understanding begs one final inevitable question. Are there any objects in the universe, any cosmic behemoths, that are truly massive enough, dense enough that we would experience significant, deeply noticeable time dilation around them? The answer, a quiet whisper from the abyss, is yes. And this is where the dance of time truly begins to get very, very noticeable to an outside observer. We've explored the subtle, almost imperceptible slowing of time near our sun and earth, a gentle whisper of gravity's touch on the cosmic clock. But now, let us drift with quiet anticipation towards the truly dramatic. There are indeed objects in the universe colossal and enigmatic, where the warping of time becomes not just a theoretical curiosity, but a profound, undeniable reality, deeply noticeable to an outside observer. These are the titans that reside at the very hearts of galaxies, the silent giants known as supermassive black holes. Imagine these cosmic behemoths not as mere points in space, but as colossal wells impossibly deep and vast, carved into the very fabric of space-time itself. Their masses are truly mind-boggling, ranging from millions to even billions of times the mass of our own comforting sun. Picture our sun, that immense sphere of fiery gas, now multiplied by 1,000,000 or even 1,000,000,000 times, and then compressed into a space smaller than our solar system. The sheer density, the unfathomable concentration of matter, creates a gravitational pull so immense, so powerful, that nothing, not even light, can escape its relentless embrace once it crosses a certain boundary. Within the profound gravitational grip of such a colossal entity, time itself can become incredibly astonishingly malleable. If you were to embark on an incredibly daring hypothetical journey towards one of these giants, gently falling deeper and deeper into its immense gravitational well time, for you could slow down so much that it would approach zero. It's like wading into a river that becomes progressively thicker, its currents heavier until it feels like flowing through molasses, then through a boundless viscous honey, and finally into something utterly frozen. The ticking of your internal clock, the beating of your own heart, the very unfolding of your personal moments would, from the perspective of a distant observer, stretch out into an agonizing, almost infinite crawl. Imagine the sheer mind-bending implications if you were able to get incredibly close to one of these cosmic giants, perhaps orbiting safely just outside its point of no return, and then miraculously manage to escape its immense gravitational pull and return to a safer, more familiar region of space. You could find that your brief foray into its vicinity had unfolded with an almost impossible disparity. You might have spent what felt like a mere half an hour in that warped, time-dilated environment, your personal clock ticking away only 30 minutes. Yet, upon your triumphant return, you could emerge to discover that hundreds of years had effortlessly passed for the people back on Earth. Their world would have spun through countless seasons. Generations would have lived and died. Entire civilizations might have risen and fallen, all while you experienced what felt like a brief, intense encounter. To those people on Earth, if they possessed a powerful enough telescope to observe your daring expedition from afar, they would see something truly surreal. They would witness your form, your tiny vessel seeming to barely move at all. Your actions, your gestures, even the subtle unconscious movements of your body would appear excruciatingly slow, like watching a film played back at an incredibly, impossibly low frame rate. Even your simple breaths would seem to take days to complete each inhale and exhale, stretching across what for them was an eternity. You would be a living, breathing testament to time's profound elasticity, a ghost from their deep past, arriving in their distant future. In fact, there would be a precise point, a theoretical boundary, right at the very edge of such a colossal body, where as you approached it, your time would, from the perspective of the outside universe, hit absolute zero. This boundary is famously known as the event horizon, the ultimate point of no return, a one-way cosmic membrane. If you were to pass that point, What would truly happen? This is where the whispers of our current understanding, the elegant equations that have guided us thus far, begin to falter. Our scientific models, our most profound mathematical descriptions of reality, break down at the event horizon, and so they cannot definitively explain what lies beyond that final enigmatic threshold. Science, as we know it, does not yet possess the complete answer to that ultimate question. Though there are certainly many fascinating, often wild theories attempting to pierce the veil of that deepest mystery, those are perhaps tales better explored in another quiet episode, another journey into the truly unknown. For tonight, we simply acknowledge the boundary and allow ourselves to wonder at its profound, silent implications. These concepts, general and special relativity, can indeed be pretty confusing topics, stretching our intuition in ways that feel almost unnatural. But was this gentle exploration, this quiet meandering through the cosmos, helpful in helping you digest this profound topic? Did it offer a sense of understanding, however fleeting, however metaphorical? And is this something you'd like to know more about? To perhaps delve deeper into the intricate dance of space-time and gravity? Please let me know your thoughts in the comments below, or simply hold them in your heart as you drift towards sleep. And if you found value in this gentle journey, if it stirred a sense of wonder within you, please consider giving it a like and subscribing, helping us to continue these quiet explorations into the unseen wonders of our universe. Now let's gently shift our focus again to another profound question, one that builds upon our understanding of time's malleability. What is time truly? In this series, we've talked a lot about time, haven't we? We've learned that as black holes warp the very fabric of space around them, time itself slows down, becoming sluggish, almost hesitant. We've discovered the time-influencing effects of gravity, a silent hand that gently tugs at the rhythm of our moments. We've even touched upon how the magnificent James Webb Space Telescope, that cosmic eye, can effectively peer through time to the distant past, capturing the faint ancient light of the universe's infancy by cleverly taking advantage of the fixed, unwavering speed of light. All of this makes a certain astonishing sense, building layer upon layer of scientific understanding. But what actually is time? You can't taste it, can you? You can't touch it, feel its texture against your skin, or truly grasp it in your hands. Yet time possesses an unstoppable, relentless influence on us all. It propels us forward whether we like it or not, an invisible current carrying us towards an unknown future. Doesn't something that impacts everything we do, every breath we take, every dream we weave, deserve some additional deeper understanding? I'm Alex McCone, and you're quietly observing with Astrom. While this is an area where scientists have many, many profound theories, each vying for a glimpse of the ultimate truth, I'd like to share with you tonight one particular model, one perspective that might gently help you understand this mysterious, elusive concept that is ticking silently all around us. By the end of this quiet reflection, we are going to have a possible, even elegant explanation for why time slows down as velocity increases, and why the familiar shapes of objects warp and contort when undergoing velocities incredibly close to the speed of light. This particular model, this gentle guiding visualization, is a collaboration with my brother, based on recognized scientific theory, where we have taken fundamental scientific concepts and woven them together into something you may not have quite seen, presented in this way before, something that offers a fresh, perhaps comforting perspective on time's elusive nature. But before we gently step into that deeper understanding, we must begin with one foundational, profoundly important idea. It's an idea that at first blush might sound like something from the most fantastical realms of science fiction. But it is in fact a cornerstone of modern physics. Time is actually another dimension. Now, before you instinctively reach out to double-check that you haven't accidentally logged into some far-flung sci-fi channel by mistake, let's calmly discuss what I truly mean by dimensions in this context. In popular culture, different dimensions are often vividly described as parallel worlds, alternate realities that are very similar to ours, yet subtly, perhaps eerily different. They conjure images of mirror universes or branching timelines. But in this profound context, when we softly talk of different dimensions, we are primarily referring to the dimensions of space, as in our familiar three-dimensional space or 3D space, which may be far more familiar and comfortable for your mind to grasp. This concept, though seemingly simple, is by no means trivial. Our 3D space is not just around you. It is the very around you, the canvas upon which your entire life unfolds, and it is profoundly relevant to our topic tonight. Let's begin by making sure we all gently understand the familiar 3Ds and the intricate relationships between them before we dare to add the elusive fourth D. Broadly speaking, 3D or three-dimensional space simply refers to space that can be measured in three different mutually perpendicular directions. Imagine three lines each, crossing the other at a perfect right angle like the corner of a room. This perpendicular nature of these dimensions is crucial, and we'll gently explore why that matters later. Three-dimensional space is usually comfortably described as having height, width, and depth, and crucially, they all exist at those precise 90-degree angles, between them forming a perfectly orthogonal grid. Simply put, objects like us that exist fully in 3D space have the freedom to move. We can move left and right across a plane, we can move up and down vertically, and we can move forwards and backwards through depth. We are perfectly comfortable with this kind of space. It is our home, our natural habitat, the very stage of our existence. Using this familiar foundation as our secure basis, it becomes much easier, much more intuitive to imagine what we mean by 2D space, and even 1D space. To gently transition from one type of space to another, all we need to do is either remove or gracefully add an extra dimension of measurement or movement. And here's the crucial rule: that added or removed dimension must always be at a 90-degree angle from all previously existing angles. So imagine a hypothetical 2D object. This object would move exclusively in a flat plane like a drawing on a piece of paper. It's bounded by, say, the X and Y directions, or perhaps the X and Z directions, or the Y and Z directions, but crucially, never all three at once. It has no up or down in the way we understand it, only across and along. Think of a character in an old video game limited to moving left, right, up, and down on a flat screen. Now imagine a truly constrained 1D object. This entity could only move either along the X-axis, or the Y-axis, or the Z-axis. Picture a person who lived their entire existence in such a 1D world. Their whole reality would be found either moving one way or the other, eternally, along a single, infinitely thin line. All of reality, everything they could possibly perceive, would exist either to their immediate left or to their immediate right, and would appear to them only as a singular luminous dot. They could not conceive of, let alone move or see, in any of the other directions that we take for granted. Photons, tiny packets of light whizzing by them, would only be visible if they happened to enter and travel along the singular line that constituted a 1D person's entire area of existence. It's a profoundly limited yet fascinating way to exist, highlighting the richness of the dimensions we inhabit. So the very act of adding extra directions of movement, always at those precise, perpendicular 90-degree angles, is precisely what's needed to move things up from 1D space to 2D space to our familiar 3D space. And by extension, in theory, we can begin to predict what we would need to do if we were to make the leap to conceptually jump to a 4D space. However, here we hit a gentle yet significant snag. While it's elegantly simple to draw a line that's perfectly perpendicular to a single other line on a flat surface, or to draw yet another line on top of those two lines that is perfectly perpendicular to both previous lines, forming the three axes of our familiar 3D space, how then would we possibly draw a fourth line that is perfectly perpendicular to all three of those? Surely such a thing is utterly impossible within the confines of our perceived 3D space, and indeed within the boundaries of our familiar 3D space. Drawing such a thing directly is impossible. Our brains wired for 3 dimensions struggle to visualize a 4th orthogonal axis. The best we can do is draw approximations, clever representations that hint at the existence of higher dimensions. For instance, it's perfectly possible, and indeed common, to draw an approximation of a 3D shape, like a cube, on a flat 2D piece of paper. By doing something like this, we use perspective overlapping lines and shading to create the illusion of depth. These lines are all fundamentally 2-dimensional, existing only on the surface of the paper. Yet when we look at this drawing, our amazing brains immediately recognize that this is a picture of a 3D shape, a mental leap that transcends the flat reality of the page. So in the same profound way, we could probably do something similar to visualize what a 4D object might look like using just our familiar 3D lines, creating an approximation that hints at its true form. Mathematicians, with their incredible abstract reasoning, have indeed attempted to do this, creating intricate diagrams and complex geometric figures that represent higher dimensional objects. Although it must be admitted, their results tend to be a little confusing, often resembling intricate overlapping shadows rather than clear forms. While this is mathematically sound as a basis for conceptualizing a 4D object, I personally don't find my intuitive understanding of 4D space significantly deepened simply by looking at such complex diagrams, so I won't focus on them in this gentle exploration. However, there is some profound evidence, a persistent whisper from the universe itself, that a 4th direction, a 4th dimension does indeed exist, and astonishingly, we are all moving along it right now. That mysterious 4th direction or dimension is none other than time. Einstein, with his unparalleled vision, predicted this profound connection when he elegantly linked space and time into one unified, inseparable entity, which he famously called space-time in his groundbreaking theories of relativity. According to his radiant insights, time and space are not distinct independent things, but rather 2 interwoven parts of the same ultimate fabric, 2 sides of the same cosmic coin. To me, this concept beautifully and seamlessly connects with the idea of 4D space. Just as there is no true fundamental difference between the z-axis and the x or y directions, they are all simply different orientations within the same 3-dimensional spatial canvas. So too, would there not be any fundamental difference between time and space if time is truly just another direction, albeit one that we currently cannot visually perceive or easily navigate in reverse? And time, we must remember, is profoundly important, isn't it? Without time, our familiar 3D space wouldn't move. It would perpetually be frozen in a single unchanging state. There would be no growth, no decay, no light, no motion, no life, because it is time that allows us to move about in it, to experience change, to dance through the moments. It's the engine of existence, the very pulse of the cosmos. We have gently explored the idea that time is not merely an abstract concept, a fleeting river that carries us forward, but rather a profound 4th dimension of our universe, a direction along which we are constantly, inexorably moving. But if time truly is a dimension, woven into the very fabric of existence like length, width, and depth, then why, we might softly ask, can we not see it in the same tangible way we perceive the height of a mountain, the width of a river, or the depth of a canyon? Why can't we simply turn our heads and catch a glimpse of yesterday, or peer into the hazy outlines of tomorrow? This question, so simple, yet so profound, guides us now to a beautiful, gentle analogy, a way to softly visualize our own ephemeral existence within the grand tapestry of space-time. Imagine, if you will, that our existence, our very being, is confined to a realm of fewer dimensions than we currently inhabit. Picture yourself as a creature living entirely within 2 spatial dimensions. You are a flatlander, perhaps a character from an old charming video game, or a drawing meticulously etched onto the surface of a vast, infinite piece of paper. You possess length and width, allowing you to move left and right or up and down across your flat world. But crucially, you have no concept of depth. You cannot perceive, interact with, or even imagine moving out of the flat surface upon which your entire life unfolds. Your reality is a canvas, and you are forever bound to its two-dimensional confines. Now into this flat two-dimensional world, imagine a three-dimensional object. A sphere like a smooth, perfectly round ball begins to pass through your flat reality. From your limited two-dimensional perspective, you would never see the entire ball at once. That full volumetric shape would remain eternally hidden from your perception. Instead, what you would experience would be a series of changing two-dimensional slices as the ball intersects your plane of existence. First, a tiny, almost imperceptible dot would appear, the very first point where the sphere touches your world. Then, as the ball descends further, that dot would expand into a small circle, then a larger circle growing steadily until it reached the widest point of the sphere. As the ball continued its passage, the circle would then begin to contract, shrinking back into a smaller circle, then a tiny dot, before finally vanishing altogether. You would never truly perceive the three-dimensional form of the ball. Only these fleeting, ever-changing, two-dimensional cross-sections of it, as it smoothly, silently passed through a dimension you are utterly incapable of perceiving. Now let's gently, with a sense of quiet awe, apply this analogy to ourselves, to our own existence. If we are beings rooted in three spatial dimensions, then perhaps in a profoundly similar way, we are also flatlanders within the larger encompassing dimension of time. Just as the two-dimensional creature could not perceive the full three-dimensional ball, we too cannot perceive our full, continuous four-dimensional shape all at once. We don't see our entire life from birth to inevitable end spread out before us as a static, unchanging form. Instead, we only experience a single three-dimensional slice of our full four-dimensional self at any given moment, and that, dear listener, is precisely what we call the present moment. We cannot see our past or our future in a direct visual sense, in the way we can look at an object in three-dimensional space and perceive its entire length, width, and depth simultaneously. Our experience is fundamentally different. We only encounter a three-dimensional cross-section of ourselves and of the universe as we move relentlessly, inevitably, along the dimension of time. Think of it like a roll of film unspooling before our eyes. Each individual frame on that film is a distinct three-dimensional slice of reality at a particular moment. As we watch the film frame by frame, we experience the seamless, continuous flow of time, the unfolding of events. But we cannot look at all the frames simultaneously. We are forever bound to the single unfolding frame of the present. The film itself exists as a whole, a complete four-dimensional entity, but our perception is limited to its fleeting successive moments. This analogy, with its gentle clarity, also helps us to intuitively understand why we cannot. It seems travel backward in time. For our two-dimensional flatlander, moving into the third dimension, that dimension of depth it cannot perceive, is an inherent impossibility. It lacks the very capacity to sense, interact with, or manipulate that dimension. Similarly, for us as three-dimensional beings, moving through the fourth dimension of time, moving backward along that temporal axis, appears to be an inherent fundamental impossibility. We are in this grand cosmic river, forever locked into a forward momentum, propelled by an unseen current. We can feel the flow, we can experience the passage, but we cannot. It seems simply turn around and swim upstream to revisit moments that have already passed. The arrow of time for us points in one direction, only forward into the ever-unfolding future. So what does this elegant visualization, this gentle whisper of time as a dimension, imply for time dilation, that astonishing phenomenon we explored when discussing the effects of extraordinary velocity and the silent, profound influence of gravity? If time truly is another dimension, then our motion within the spatial dimensions can indeed profoundly affect our motion within the temporal dimension. Imagine, if you will, that you possess a finite, fixed amount of total speed, or total motion, that you must somehow distribute like a cosmic budget between all the dimensions of space-time. This total speed is equivalent to the ultimate cosmic speed limit, the speed of light. Every particle, every being is always moving at the speed of light through space-time, even if it's stationary in spatial terms. If you choose to allocate more of your total speed budget to moving through spatial dimensions, meaning you accelerate and travel faster through space, then by necessity, you will have less of that total speed available to allocate to moving through the temporal dimension. The balance must be preserved. This implies that you will, from an external perspective, move slower through time. It's like having a fixed amount of fuel for a journey. If you use more fuel to go very fast in one direction, say horizontally across a flat plane, then you have less fuel remaining for vertical movement. In a more profound cosmic echo, when we dedicate more of our inherent space-time velocity to speeding through the familiar spatial dimensions, our velocity through the time dimension must commensurately decrease. This, in essence, is the very heart of time dilation. Your internal clock, your experience of moments, begins to run more slowly, relative to someone who is using more of their total speed budget to move primarily through time rather than through space. Consider it as if you are driving a car with a fixed top speed. If you drive perfectly straight on a highway, all your speed is directed forward. But if you begin to turn the wheel, engaging in constant sharp turns to the left and right, or driving in circles, your speedometer might still read your top speed, but your actual net forward progress along the road will be much slower. You're using your speed to change direction to accelerate in other spatial dimensions, rather than purely moving forward. Similarly, when we move faster through space, we are tilting our velocity vector, that fixed total speed we possess in spacetime, away from the pure time axis and more towards the spatial axis. As we tilt more and more towards space, our component of motion along the time axis naturally shrinks. This results in the observed slowing of time for the fast-moving object. This profound concept also elegantly explains why the speed of light itself is the ultimate unattainable limit for anything with mass. A photon, a particle of light, is inherently always moving at the absolute maximum possible total speed within spacetime. This means that all of a photon's total speed budget is fundamentally allocated to moving through the spatial dimensions. If every single bit of its inherent spacetime velocity is distributed into traversing space, then there is absolutely no remaining velocity to be allocated to moving through the temporal dimension. Consequently, from the perspective of anything else in the universe, time simply stops for a photon. From its own non-existent perspective, it is born and absorbed simultaneously, regardless of the staggering light years it might traverse in space. It is a timeless traveler, a pure expression of spatial motion, an eternal moment of luminous existence. Furthermore, this beautifully simple yet profound analogy can also help us gently visualize length contraction, another mind-bending effect predicted by special relativity. When an object moves faster and faster through space, it appears to contract or shorten along the direction of its motion from the perspective of a stationary observer. If time is indeed a dimension, then this spatial contraction can be intuitively understood as a subtle yet significant rotation within the combined fabric of spacetime. When an object increases its speed in space, it is not merely moving faster. It is also, in a profound sense, subtly rotating its inherent spacetime form within the four dimensions. This rotation means that the object, from an outside perspective, appears shorter along its direction of travel. Much like a three-dimensional rod appears shorter if you view it at an angle rather than directly face-on. It's an illusion born of perspective and the interconnectedness of space and time as the object's form is tilted further into the time dimension, presenting a foreshortened spatial view to an external observer. All of these profound concepts, when contemplated with a sense of quiet wonder and a gentle receptive mind, paint a portrait of a universe that is astonishingly flexible, far more dynamic and responsive than our everyday experiences might suggest. The seemingly rigid stage of space and the unwavering arrow of time are in fact fluid elements capable of bending, stretching, and warping in response to motion and mass. It's a universe that is not just a static backdrop for events, but an active participant, a responsive canvas upon which the cosmic drama unfolds. This deeper understanding invites us to let go of our ingrained assumptions and embrace a reality that is far richer, far more intricate, and far more awe-inspiring than we could ever have imagined. It encourages us to look beyond the surface to feel the subtle currents of space-time and to marvel at the profound elegance of the laws that govern everything we know. We've journeyed through the subtle shifts in time caused by our planet and our sun, mere whispers in the grand cosmic symphony. Now let's gently guide our thoughts towards the truly dramatic. There exist objects in the universe colossal and enigmatic, where the warping of time becomes not just a theoretical curiosity, but a profound, undeniable reality, a breathtaking distortion that would be deeply noticeable to anyone observing from afar. These are the titans that silently reside at the very hearts of galaxies. The cosmic giants, known as supermassive black holes, imagine these gargantuan entities not as mere points of unimaginable density, but as colossal, impossibly deep wells carved into the very fabric of space-time itself. Picture the most immense vortex you can conceive, not of water, but of reality. Their masses are truly mind-boggling, scaling from millions to even billions of times the mass of our own comforting sun. Take a moment to truly envision that our sun, that immense sphere of fiery gas that dominates our sky, now multiplied by 1,000,000 or even 1,000,000,000 times, and then impossibly compressed into a space smaller than our entire solar system. The sheer density, the unfathomable concentration of matter within such a volume, creates a gravitational pull so immense, so powerful, that nothing, absolutely nothing, not even light itself, that swift messenger of the cosmos, can escape its relentless embrace once it crosses a certain critical boundary. Within the profound, inescapable gravitational grip of such a colossal entity, time itself can become incredibly astonishingly malleable. It stretches, it bends, it distorts in ways that defy our ordinary intuition. If you were to embark on an incredibly daring hypothetical journey towards one of these cosmic giants, gently falling deeper and deeper into its immense gravitational well time for you, would from the perspective of a distant observer slow down so much that it would approach zero. Imagine wading into a vast unseen river whose currents become progressively thicker, more viscous. At first, it feels like flowing through molasses, then through a boundless, infinitely thick honey, and finally into something utterly irrevocably frozen. The ticking of your internal clock, the steady beating of your own heart, the very unfolding of your personal moments would, when viewed from afar, stretch out into an agonizing, almost infinite crawl. Your brief journey would unfold in their eons? Imagine the sheer mind-bending implications of such a scenario. If you were able to get incredibly tantalizingly close to one of these cosmic giants, perhaps orbiting safely just outside its ultimate point of no return, the event horizon, and then by some miracle of future technology, manage to escape its immense gravitational pull and return to a safer, more familiar region of space, you would find that your brief foray into its vicinity had unfolded with an almost impossible disparity. You might have spent what felt like a mere half an hour in that warped, time-dilated environment. Your personal clock ticking away only 30 minutes, your experiences condensed into a fleeting moment. Yet, upon your triumphant return, you could emerge to discover that hundreds of years had effortlessly passed for the people back on Earth. Their world would have spun through countless seasons, entire generations would have lived and died, empires might have risen and fallen, and civilizations transformed beyond recognition, all while you experienced what felt like a brief, intense, almost instantaneous encounter. It is the ultimate journey into the future, a one-way ticket through the river of time, a bittersweet testament to the universe's extraordinary flexibility. To those people on Earth, if they possessed a powerful enough telescope to observe your daring expedition from afar, a theoretical lens capable of piercing the vast distances of the cosmos, they would witness something truly surreal, something that would challenge their every notion of reality. They would observe your form, your tiny vessel appearing to barely move at all, your actions, your gestures, even the subtle unconscious movements of your body. The blink of an eye would seem excruciatingly slow, like watching an ancient film played back at an incredibly, impossibly low frame rate. Each movement would stretch into an eternity. Indeed, even your simple breaths would seem to take days to complete each inhale and exhale, stretching across what for them was an eternity of silence and waiting. You would be a living, breathing testament to time's profound elasticity, a silent, time-traveling ghost from their deep past, arriving in their distant, altered future. In fact, there would be a precise, theoretical boundary, a cosmic membrane right at the very edge of such a colossal body, where as you approached it, your time would, from the overwhelming perspective of the outside universe, hit absolute zero. This boundary, this ultimate point of no return, is famously known as the event horizon. It is a one-way cosmic membrane, a threshold from which nothing, not even light, can escape. If you were to cross that point, what would truly happen to you, to your sense of self, to the very fabric of your being? This is where the whispers of our current understanding, the elegant equations that have guided us thus far through the mysteries of space and time, begin to falter. Our scientific models, our most profound mathematical descriptions of reality, break down at the event horizon. They simply cannot definitively explain what lies beyond that final enigmatic threshold. Science, as we currently understand it, does not yet possess the complete answer to that ultimate question. Though there are certainly many fascinating, often wild and sometimes terrifying theories, attempting to pierce the veil of that deepest mystery. Ideas ranging from being spaghettified into a stream of atoms to emerging into an entirely new universe. Those are perhaps tales better explored in another quiet episode, another journey into the truly unknown. The realm where even our most brilliant minds humbly admit they have no definitive map. For tonight, we simply acknowledge the boundary and allow ourselves the profound luxury of wondering at its silent, terrifying, yet utterly captivating implications. These concepts, general and special relativity, can indeed be pretty confusing topics, stretching our intuition in ways that feel almost unnatural, like trying to comprehend a color we've never seen. But was this gentle exploration, this quiet, meandering through the cosmic unknown, helpful in helping you digest this profound topic? Did it offer a sense of understanding? However fleeting, however metaphorical. Did it stir a quiet sense of awe within you for the universe's hidden workings? And is this something you'd like to know more about? To perhaps delve deeper into the intricate dance of space-time and gravity, allowing your mind to dance along with them? Please let me know your thoughts in the quiet comments below, or simply hold them in your heart as you drift towards the realm of sleep. And if you found value in this gentle journey, if it stirred a sense of wonder within you, please consider giving it a like and subscribing, helping us to continue these quiet explorations into the unseen wonders of our universe. Now let's gently shift our focus once more to another profound ancient question, one that builds upon our understanding of time's malleability and prepares us for even deeper mysteries. What is time truly? In this series, we've talked a lot about time, haven't we? It's been a constant, albeit elusive, companion. We've learned that as the immense gravity of black holes warps the very fabric of space around them, time itself slows down, becoming sluggish, almost hesitant, as if struggling to escape the gravitational embrace. We've discovered the time-influencing effects of gravity, a silent, invisible hand that gently tugs at the rhythm of our moments, slowing them down ever so slightly. We've even touched upon how the magnificent James Webb Space Telescope, that awe-inspiring cosmic eye, can effectively peer through time to the distant past, capturing the faint ancient light of the universe's infancy by cleverly taking advantage of the fixed, unwavering speed of light, allowing us to witness events that unfolded billions of years ago. All of this makes a certain astonishing sense, building layer upon layer of scientific understanding, each revelation adding to the grand tapestry of our knowledge. But what actually is time at its most fundamental core? You can't taste it, can you? You can't touch it, feel its texture against your skin, or truly grasp it in your hands. It has no discernible weight, no color, no scent. Yet time possesses an unstoppable, relentless, all-encompassing influence on us all. It propels us forward, whether we consciously choose it or not, an invisible, inexorable current, carrying us towards an unknown future. Doesn't something that impacts everything we do, every breath we take, every dream we weave, every fleeting thought that crosses our minds, deserve some additional deeper understanding, a more profound contemplation? I'm Alex McCone, and you're quietly observing with Astrom, drifting through the cosmic currents. While this is an area where scientists have many profound theories, each one a luminous thread woven into the vast tapestry of cosmic thought. Each theory vying for a deeper glimpse of the ultimate truth, I'd like to share with you tonight one particular model. It is a perspective, a gentle guiding visualization that might softly help you understand this mysterious, elusive concept that is ticking silently, persistently all around us. By the end of this quiet reflection, this gentle, imaginative journey, we are going to have a possible, perhaps even elegant explanation for why time slows down as velocity increases, why those distant clocks lag behind ours, and why the familiar shapes of objects, those solid forms we take for granted, seem to warp and contort when undergoing velocities incredibly close to the speed of light. This particular model, this gentle guiding visualization, is a collaboration with my brother, and it is firmly based on recognized scientific theory. We have taken fundamental scientific concepts and gently woven them together into something you may not have quite seen presented in this way before, something that offers a fresh, perhaps comforting perspective on time's elusive and often perplexing nature. It's a way to feel the quantum hum of reality. But before we gently step into that deeper understanding, before we open that particular cosmic door, we must begin with one foundational, profoundly important idea. It's an idea that at first whisper might sound like something plucked directly from the most fantastical realms of science fiction, something too outlandish to be real. Yet it is in fact a cornerstone of modern physics, a fundamental truth that underpins much of our understanding of the universe. Time is actually another dimension. Now, before you instinctively reach out to double-check that you haven't accidentally logged into some far-flung sci-fi channel by mistake, before your mind recoils from the seemingly impossible, let's calmly, gently discuss what I truly mean by dimensions in this specific context. In popular culture, different dimensions are often vividly described as parallel worlds, alternate realities that exist alongside our own, perhaps very similar to ours, yet subtly, perhaps eerily different in key ways. They conjure images of mirror universes, or branching timelines, or hidden realms. But in this profound context, when we softly talk of different dimensions, we are primarily referring to the dimensions of space. As in our familiar three-dimensional space, or 3D space, which may be far more familiar and comfortable for your mind to grasp, being the stage upon which your entire life unfolds. This concept, though seemingly simple, is by no means trivial. Our 3D space is not just around you. It is the very around you, the boundless canvas upon which your entire life is painted, and it is profoundly relevant to our topic tonight. Let's begin by making sure we all gently understand the familiar 3Ds and the intricate relationships between them before we dare to add the elusive fourth D. Broadly speaking, 3D, or three-dimensional space, simply refers to space that can be measured in three different mutually perpendicular directions. Imagine three perfectly straight lines, each crossing the other at a perfect right angle, like the crisp, clean corner of a well-built room, or the axes on a graph paper extending into depth. This perpendicular nature of these dimensions is crucial, and we'll gently explore why that matters later in the unfolding of our cosmic story. Three-dimensional space is usually comfortably described as having height, width, and depth, and crucially, they all exist at those precise 90-degree angles between them, forming a perfectly orthogonal, infinitely extending grid that defines our reality. Simply put, objects like us that exist fully in 3D space have the freedom to move in a multitude of ways. We can move left and right across a plane. We can move up and down, vertically defying gravity for a moment, and we can move forwards and backwards through depth, pushing through the space in front of us. We are perfectly comfortable with this kind of space. It is our home, our natural habitat, the very stage upon which our entire existence is choreographed. Using this familiar foundation as our secure basis, our comfortable launching pad, it becomes much easier, much more intuitive to imagine what we mean by 2D space and even 1D space, to gently transition from one type of space to another, to conceptually step into different realities. All we need to do is either remove or gracefully add an extra dimension of measurement or movement. And here's the crucial rule. The silent law that governs these dimensional shifts, that added or removed dimension, must always be at a 90-degree angle from all previously existing angles. So imagine a hypothetical 2D object. This object would move exclusively in a flat plane, like a drawing meticulously rendered on a piece of paper, or a shadow dancing on a wall. It's bounded by, say, the X and Y directions, or perhaps the X and Z directions, or the Y and Z directions, but crucially, never all three at once. It has no up or down in the truly vertical way we understand it, only across and along. Think of a character in an old pixelated video game limited to moving left, right, up, and down on a flat screen, forever confined to their two-dimensional canvas. Now stretch your mind a little further and imagine a truly constrained 1D object. This solitary entity could only move either along the x-axis or the y-axis or the z-axis. Picture a person who lived their entire existence in such a 1D world, a world reduced to a single, infinitely thin line. Their whole reality would be found either moving one way or the other eternally along that solitary, unyielding line. All of reality, everything they could possibly perceive, would exist either to their immediate left or to their immediate right, and would appear to them only as a singular luminous dot. They could not conceive of, let alone move or see, in any of the other directions that we take for granted in our rich 3D world. Photons, those tiny packets of light whizzing by them, would only be visible if they happened to enter and travel precisely along the singular line that constituted a 1D person's entire area of existence. It's a profoundly limited yet fascinating way to exist, isn't it? A thought experiment that powerfully highlights the richness and complexity of the dimensions we inhabit. So the very act of adding extra directions of movement, always at those precise, perpendicular 90-degree angles, is precisely what's needed to move things up from a meager 1D space to a more expansive 2D space, and then to our familiar, comfortable 3D space. And by extension, in theory, we can begin to predict what we would need to do if we were to make the profound leap to conceptually jump to a 4D space. However, here we hit a gentle, yet significant snag. While it's elegantly simple to draw a line that's perfectly perpendicular to a single other line on a flat surface, or to draw yet another line on top of those two lines that is perfectly perpendicular to both previous lines, forming the three orthogonal axes of our familiar 3D space, how then would we possibly draw a fourth line that is perfectly perpendicular to all three of those? Surely such a thing is utterly impossible within the confines of our perceived 3D space, which has no extra direction to offer. And indeed, within the very boundaries of our familiar 3D space, drawing such a thing directly is impossible. Our brains wired for 3 dimensions struggle mightily to visualize a fourth orthogonal axis, a direction that has no counterpart in our sensory experience. The best we can do is draw approximations, clever representations that hint at the existence of higher dimensions, much like a 2-dimensional drawing can hint at a 3-dimensional object. For instance, it's perfectly possible, and indeed common, to draw an approximation of a 3D shape, like a cube, on a flat 2D piece of paper. By doing something like this, we use perspective overlapping lines and shading to create the illusion of depth. These lines are all fundamentally 2-dimensional, existing only on the surface of the paper. Yet when we look at this drawing, our amazing brains immediately recognize that this is a picture of a 3D shape, a mental leap that transcends the flat reality of the page. So in the same profound way, we could probably do something similar to visualize what a 4D object might look like using just our familiar 3D lines, creating an approximation that hints at its true unknowable form. Mathematicians, with their incredible abstract reasoning and boundless imagination, have indeed attempted to do this, creating intricate diagrams and complex geometric figures that represent higher dimensional objects. Although it must be admitted their results tend to be a little confusing to the uninitiated eye, often resembling intricate overlapping shadows or complex knots rather than clear discernible forms. While this is mathematically sound as a basis for conceptualizing a 4D object, I personally don't find my intuitive understanding of 4D space significantly deepened simply by looking at such complex diagrams, so I won't focus on them in this gentle exploration. Our aim is clarity, not confusion. However, there is some profound evidence, a persistent whisper from the universe itself, a compelling hint that a fourth direction, a fourth dimension does indeed exist. And astonishingly, we are all moving along it right now every single moment of our lives. That mysterious fourth direction or dimension is none other than time. Einstein, with his unparalleled vision, his almost prophetic insight, predicted this profound connection when he elegantly linked space and time into one unified, inseparable entity, which he famously called space-time in his groundbreaking theories of relativity. According to his radiant insights, time and space are not distinct independent things, like separate ingredients in a recipe, but rather 2 interwoven parts of the same ultimate fabric, 2 sides of the same cosmic coin. They are fundamentally intertwined. To me, this concept beautifully and seamlessly connects with the idea of 4D space. Just as there is no true fundamental difference between the z-axis depth and the x-width or y-height directions, they are all simply different orientations within the same 3-dimensional spatial canvas, equally valid ways to measure movement. So too would there not be any fundamental difference between time and space if time is truly just another direction, albeit one that we currently cannot visually perceive or easily navigate in reverse. And time, we must remember, is profoundly important, isn't it? Without time, our familiar 3D space wouldn't move. It would perpetually be frozen in a single unchanging static state. There would be no growth, no decay, no light, no motion, no life. The universe would be a grand inert sculpture. Because it is time that allows us to move about in it, to experience change, to dance through the moments, to unfold, to become. It's the engine of existence, the very pulse of the cosmos, the silent rhythm that governs all. We've spent quiet moments contemplating time as a dynamic dimension, a river we are constantly flowing through. Now let's gently turn our attention to the perplexing, often mind-bending world of quantum mechanics, where the rules of our everyday universe seem to bend and sometimes even break. It's a realm of whispers and probabilities, a place where light, that swift and constant messenger, reveals even more layers of its mysterious nature. First, let's reconsider that steadfast beacon of the cosmos, the speed of light. In the grand sweeping canvas of our universe, the speed of light in a vacuum, that vast empty darkness between stars, is held as an absolute constant, the ultimate cosmic speed limit. It's the highest note in the universe's symphony, a fundamental unwavering benchmark. Regardless of how fast you might be moving or in what direction, if you measure the speed of a beam of light in the emptiness of space, it will always be precisely the same, approximately 299,792,458 meters per second. This is a core tenet of Einstein's relativity, a truth so profound that space and time themselves will warp and bend just to ensure light's speed remains fixed. It's as if the universe has a perfectly calibrated cosmic odometer for light, and it never ever wavers. However, we've known for a long time that as soon as you introduce matter into light's pristine path, things get a little different. Light gets bogged down. It slows its tireless pace like a runner trying to sprint through a dense, unseen fog. Light traveling through air, for instance, only moves at roughly 299,705,000 meters per second, a full 87th or 458 meters per second, slower than its speed in a vacuum. Dip that light into water, and it slows even further to around 225 million meters per second. And if you send it through glass, it caps out at a sluggish 200 million. The reasons for this seemingly mundane slowing are intriguing, yet fairly well understood, and certainly not physics-breaking in a paradoxical sense. Imagine light as a wave, a gentle undulation of electromagnetic fields. When this wave travels through matter, it's constantly interacting with the electrons within that material. These electrons, like tiny ships, bobbing on the surface of a restless ocean, are set into motion by light's oscillating electromagnetic fields. But here's the clever part. As these electrons move up and down, they, too, generate their own miniature electric fields, which in turn create their own tiny magnetic fields. In essence, these vibrating electrons become secondary sources of light. A second light wave is created by these moving particles, a phantom wave echoing the original. Crucially, this secondary wave perfectly overlaps the waves of the original light, but with a subtle twist, it waves at a slightly different pace, a subtly altered rhythm compared to the original light. The exact speed of this interaction, and thus the resulting slowdown, varies depending on the specific properties of the material. When these two waves, the original light wave and the new wave generated by the electrons meet, they interfere with each other. Think of two sets of ripples on a pond. Sometimes they combine constructively to build each other up, creating a larger crest. Other times, they work against each other destructively, interfering, flattening each other out. When you take the grand total, the average of all the ups and downs of each wave, you actually end up with a new composite wave, one that travels at a different speed to the original two, and one that consistently goes slower than the speed of light in a vacuum. Eventually, this composite propagating wave can reach the edge of the blocking material. Without those eager electrons to interfere anymore, you're left with just the original light again now, free to travel along its original path, at its original unburdened speed, as if nothing had ever happened. It's a beautiful, elegant dance of interaction, a temporary detour for light, but one fully explained by our understanding of its wave-like nature. Scientists have had a lot of fun and made some truly astonishing discoveries, playing with this concept over the years. In 1999, a remarkable researcher named Lainey Howe, working at Harvard, was able to slow down light to an astonishing 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to an incredibly frigid 1/1000th of a degree above absolute zero. Imagine light, that fastest entity, reduced to the speed of a bicycle. Then just 2 years later, in 2001, Howe and her team managed to achieve an even more incredible feat. They brought the speed of light to an absolute zero, literally stopping it dead in its tracks within the cloud, before gently warming up the cloud and sending the light on its way again. It was as if time itself had paused for the light beam, a truly mesmerizing demonstration of light's pliable nature within exotic mediums. You might find those results incredibly surprising, perhaps even defying belief. However strange things have happened, not just in the direction of slowing light down, but in the opposite direction too. In the year 2000, researchers at the NEC Research Institute in Princeton, New Jersey, conducted an experiment where they sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed impossibly that it exited before it had even entered. This result on the surface might appear to mess profoundly with causality, that fundamental law that causes must precede effects. How can you leave a building before you go inside it after all? Fortunately for our sanity and the consistent laws of the universe, there was a simple, elegant explanation that saved us from creating too many paradoxes. Though it highlights the subtle complexities of light, while the light pulse appeared to travel faster than light, the light itself, the actual information carried by any individual photon, did not. This was more an optical illusion than a fundamental refutation of Einstein's relativity. To understand this subtle distinction, let's take a closer look at what a photon of light truly represents. Each photon is like a tiny, intricate packet of waves moving up and down, oscillating through space. The speed at which these individual waves inside the packet propagate is known as its phase velocity. This is the speed of the crests and troughs of the wave itself. However, the speed at which the packet as a whole, this little bundle of energy and information, is traveling, is known as the group velocity. You can also have a wavefront velocity, which is how fast the very first photon, the leading edge in a wave of photons, can travel. This might sound a little heavy in its terminology, a bit like academic jargon. So let's explain it with a more intuitive example, a beautiful analogy that sheds light on the distinction. Think of a large crowd of people gathered in a stadium doing a Mexican wave. The wave that the people are doing, hands rising and falling in a continuous ripple, is analogous to the phase velocity. You can see this wave traveling along through the crowd at a seemingly rapid speed, propagating from one end to the other. It might look like it's moving incredibly quickly across the stadium. However, the crowd itself, the actual people, the physical mass, isn't going anywhere. They are simply standing in place, oscillating. So the crowd's true speed, its physical velocity across the ground, is essentially zero. These people, in their collective motion, represent the group velocity, or perhaps, if we're talking about the very first person, to start the wavefront velocity. Now let's imagine that we wanted to send our crowd marching across a field while simultaneously performing their Mexican wave. They could certainly do so. They could walk forward keeping their formation and continue doing their wave as they traveled. But although they're waving hands, the phase velocity of the wave might make the wave appear to go really fast in the direction of their travel. It would effectively vanish whenever it reached the front of the marching crowd. The information carried by the wave, the message of the wave itself, couldn't go faster than the actual walking speed of the crowd itself, the group velocity. Regardless of how fast the peaks in the wave seemed to be traveling, no actual message could be delivered until the first person in the physical crowd arrived. Einstein, in his profound theory of relativity, never claimed that phase velocity couldn't exceed light speed. His groundbreaking claim was that information couldn't travel faster than light. And if you're trying to deliver a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast their hands are waving until the first physical person in the crowd arrives. No new information can be delivered until the actual material medium reaches the destination. Still, this subtle but crucial difference between the waves within light phase velocity and the speed of light itself as an information carrier group velocity will become incredibly interesting and profoundly strange in our next thought experiment. And this is where things truly start to get a little weird. Oh, you thought it was weird already? Oh no, my curious friend. This is where we venture into the really physics-defying part, where our intuition might truly begin to unravel, and the universe whispers its deepest, most enigmatic secrets. Let's gently go back to an experiment we've looked at before. A cornerstone of quantum mechanics, a thought experiment that has captivated minds for generations. The double-slit experiment? If you're not familiar with it, imagine a barrier with two tiny parallel slits cut into it. When you fire a stream of particles like electrons at this barrier, you expect them to pass through one slit or the other and create two distinct piles on a screen behind it, like firing marbles at a fence. Simple enough. But when you fire individual particles one by one, a truly astonishing thing happens. They begin to create an interference pattern on the screen, a series of bright and dark bands, just as if they were waves. This implies that each particle somehow must be passing through both slits simultaneously and interfering with itself. It's a fascinating exploration of how light, and indeed all quantum particles, can sometimes behave like a wave and sometimes like a particle, a profound duality that continues to mystify. However, in 2023, a brilliant team of researchers from the Imperial College in London figured out a way to subtly yet profoundly alter this classic experiment. They managed to separate the slits of this experiment not in space, as is traditionally done, but incredibly in time. Imagine that. Instead of two physical openings next to each other, they created two openings in the very fabric of time itself. The way they accomplished this was remarkably ingenious yet elegantly simple in principle. They took a transparent material, a rather mundane-sounding substance called indium tin oxide. This material, which you might surprisingly find in most mobile phone screens, has a peculiar property under very specific controlled conditions. It can be made to rapidly switch from being transparent to being reflective and then back again. It's like having a window that can instantly become a mirror. The researchers fired a single precise laser pulse at this indium tin oxide material. Then, with incredible speed and precision, they rapidly changed the material from transparent to reflective, and then almost instantly back to transparent again. This rapid fluctuation created only a slim fleeting window, just a few femtoseconds long. A femtosecond is 1/quadrillionth of a second, an unimaginably short span of time during which the laser pulse was actually reflected. They called this fleeting moment, this brief window of reflectivity, a time slit. They carefully recorded what the single laser pulse looked like after it had been reflected through this ephemeral time slit. What they found was that its frequency had spread out a little bit in the process, like a musical note, slightly broadening its range. But other than that, nothing too crazy had happened. It seemed like a relatively straightforward interaction between light and matter. The real mind-bending weirdness began when they sent two separate laser pulses through these incredibly precise time slits in rapid succession. The physical setup, the position of the laser emitter, the mirror, and the receiver that detected the light all remained perfectly the same, fixed and unmoving in space. The only thing different was the precise timing when the first laser pulse went through its time slit, and then a fraction of a femtosecond later, when the second laser pulse went through its own distinct time slit. Oddly enough, and this is where the universe truly began to whisper its secrets, when two pulses went through these temporally separated slits, an interference pattern happened. But this was not an interference pattern in the same sense as with the regular 3D space double-slit experiment, where you see alternating bright and dark bands of intensity. No, this was an interference pattern that had profoundly affected the laser's frequency. Certain specific frequencies of light within the laser pulse faded out, disappearing as if canceled, while others remained. And this fading out happened exactly in line with the way intensity faded out in the regular spatial version of the double-slit experiment. It was as if the wave nature of light, usually expressed in its spatial interference, was now being expressed in its temporal interference, a dance of frequencies rather than locations. To visualize why this might be happening, let's gently draw out this experiment in regards to time itself. The time slit experiment can be depicted in a similar elegant way to the traditional double slit experiment. Except now, we are going to need to explicitly visualize the change in the experiment over time. To do that, let's create a conceptual 4D graph, where our familiar space is represented along the x-axis stretching horizontally and time is represented along the y-axis, stretching vertically upwards. It's a simple visual trick and intuitive way to map events in space-time. On this graph, it looks something like this. A photon leaves the emitter to the left, travels across space, and time hits. The time slit is reflected and then continues its journey, finally arriving at the receiver on the right. I've drawn this as a continuous smooth line, a single trajectory, just to make things simpler for our gentle understanding later. But the underlying idea works just as well either way. Later, a second photon is released from the emitter. It follows a similar path. It reflects off its own time slit and arrives at the receiver at a slightly later time, which is represented by its position higher up, further into the future, on our time graph. If light behaved normally in a purely classical, predictable sense, simply traveling along at the constant speed it was supposed to go at, this would be the end of it. Each photon would simply follow its own direct linear path through space-time, arriving sequentially. Instead, something utterly profound and perplexing is occurring. Light is interfering with itself. This means that for the interference pattern to emerge, for the frequencies to cancel out in such a precise, wave-like manner, light must somehow be traveling along a path that takes it not just through its own time slit, but also, paradoxically, through the other time slit as well. It's as if a single photon, a single packet of light, is somehow aware of all possible temporal paths it could take and explores them all simultaneously, interfering with its own possibilities. This is the only way that light could come in with the specific wave-like pattern of canceled frequencies that we observe. And just like in the classic double-slit experiment, it's highly likely that this quantum exploration is happening on the other side of the slits too, with light exploring all possible future paths. As for why it's the frequency of light and not its intensity that's being messed with here, why certain colors are fading out, rather than simply being brighter or darker. Think about the profound implications of what you might see if light did indeed come in at a different angle through this space-time graph. Photons, as I've previously mentioned, come in little packets of waves like miniature energy ripples. Now look at what happens conceptually. If you subtly change the angle at which those waves arrive at the receiver, if their path through space-time is slightly altered, here's how it normally might look: a steady rhythmic arrival of wave peaks. I've added a black timeline here and have highlighted every time the receiver perceives a new peak in the light wave. Now imagine what happens when you alter the direction of the wave's arrival, when its trajectory through space-time is subtly bent. Suddenly, the peaks are coming in much more frequently, compressing in time. The frequency of a wave over time is very much connected to the color we perceive light to be. Lower frequency light appears redder in color, while increasing the frequency shifts light's color towards the blue end of the spectrum. So this observed color variation, this subtle shifting of frequencies, makes profound sense in this context. What makes less intuitive sense, what truly challenges our deeply ingrained understanding of reality, is what's going on with the very paths this light is taking through time. Remember, the straight lines we started with on our 4D graph represent the constant speed of 299, 792, 438 meters per second, the speed we see light traveling in a vacuum. So what can we truly say about the photons that are traveling along these interference paths, these apparent alternative routes through space-time? For some parts of their journey, it appears they are traveling slower than the speed of light, taking more time to arrive at a destination that is the same spatial distance away. They are lagging behind, almost dragging their feet through the cosmic fabric. And yet, for other parts of their journey, astonishingly, they are traveling faster than causality ought to allow. From their perspective, if such a thing could be described, they are traveling backwards in time. As a gentle reminder, those two emitters on the left of our 4D graph are not actually separate emitters, but rather the same one, just at different points in time. The same holds true for the receivers on the right. This is a mind-bending result, a profound whisper from the quantum realm, And yet, according to the meticulously performed results of this experiment by the research team at the Imperial College in London, this is precisely what is occurring. Light in its deepest nature seems to be exploring paths that defy our linear understanding of time. The implications of this are truly startling, inviting us to rethink fundamental assumptions. It suggests that light in its eternal wisdom always travels the path of least time, the route that allows it to arrive at its destination along the path closest to its fixed speed in a vacuum. It's a principle known as Fermat's principle, but here it's infused with a new temporal depth. And yet it seems that in its tireless efforts to locate exactly what path that might involve light, is constantly testing the waters, putting out subtle feelers or probing waves that check to see if other paths, and seemingly other paths through time itself, might present a more viable, more efficient solution. These probabilistic feelers are not just interfering with photons that travel alongside them in the present moment, but also with photons that travel a little ahead or behind them in time. To be clear, we never actually detect photons taking any of these other strange paths. We don't see photons visibly coming in from the future. We never observe photons traveling slower than the speed of light provided. There are no supercooled gases or exotic materials, providing an obvious explanation for why they might slow down. And yet, for these intricate interference patterns to occur for those specific frequencies, to cancel out so precisely to at least some profound extent, light must be trying out these alternative routes through time. Perhaps it's like a flash of lightning, which doesn't just follow a single predetermined path. Instead, it seems to test many different directions simultaneously, sending out numerous faint tendrils probing the air to find the optimal, least resistant path for its destination before finally finding the one that works and collapsing down that specific path in one giant instantaneous boom. All the other exploratory feelers, those whispers of alternative paths, simply vanish and collapse back into the quantum foam. Or perhaps some other even more profound phenomenon, one that lies beyond our current grasp, is at play here. Who can truly say for now? All we know is that light in its endless mystery has proved once again that it doesn't play by anyone's rules, at least not rules that we, with our limited human perceptions, can fully figure out. It dances to a cosmic rhythm that we are only just beginning to discern. We've journeyed through the astounding realm of light's seemingly impossible paths, hinting at a universe far more interconnected than we perceive. This leads us to the final, most baffling question in our exploration tonight. Can information truly travel backwards in time? It's the sort of thing that would be incredibly, unbelievably useful if it were true, wouldn't it? Imagine the possibilities. You could gently whisper a warning to your past self, not to eat that questionable burrito that didn't quite agree with you, saving yourself a night of discomfort. Or more dramatically, you could reveal to yourself the winning lottery numbers for next week, securing an instant fortune. But as we instinctively know, these things simply don't happen in our everyday reality. The resulting paradoxes alone, the dizzying loops and inconsistencies that would ripple through causality, would make the whole concept utterly laughable in our universe. Here, time always seems to flow in one undeniable direction, forward relentlessly, like a cosmic river. The idea of truly traveling backwards in time, or even simply communicating with your past self, seems so outlandish, so utterly impossible, that it can't possibly be true in our grand orderly cosmos. So why is it then that on the quantum level, within the bizarre ephemeral dance of subatomic particles, information seems to be doing just this? What you might ask, you haven't noticed particles communicating backwards in time in your daily life. Well, perhaps we need to gently dip our toes into the profound strangeness that is quantum mechanics. It is a field where intuition often fails, and reality plays by rules we are only just beginning to decipher. It is an effect that, if understood and harnessed, could one day potentially bring us technologies that currently exist only in the wildest dreams of science fiction, like faster-than-light communication, or even perhaps faster-than-light travel. But even if we never manage to harness its raw power, it remains an undeniably strange, beautiful, and deeply insightful peek into the unseen world that underpins everything around us, a world far more mysterious than we could ever imagine. I'm Alex McCone, and you're quietly observing with Astrom. Tonight you're about to hear about some real-world experiments meticulously conducted by brilliant minds that are mind-bendingly weird, pushing the very boundaries of our understanding. And if by the end of this gentle journey you enjoyed what you learned, if it stirred a sense of wonder, feel free to give this video a like and subscribe to the channel. Just please don't break causality when you do so. So, what do I mean by particles traveling backwards in time or seemingly communicating across it? By all conventional accounts, it doesn't seem possible. In previous discussions, we established that objects would require an infinite amount of energy to even go fast enough to merely reach the speed of light, let alone exceed it. So, how then could something possibly go so fast as to reverse the usual direction of time to arrive at a destination, not just instantly, but before they even left their starting point? Not even light, the fastest thing we know of, can truly do that in terms of carrying information. Well, this rule about nothing traveling faster than light is mostly true for the macroscale universe that we live in, the world of tables, stars, and people, everything significantly larger than an atom. But a brilliant physicist named John Stuart Bell noticed an extraordinary exception to this rule, an exception that emerges when it comes to quantum entangled particles. Okay, so let's gently begin there. What exactly is a quantum entangled particle? In the profound, often bewildering realm of quantum physics, it's possible to interact with two particles in such a precise and delicate way as to link them together to bind their fates, so that by measuring certain properties of one particle, you instantly learn things about the other, no matter how far apart they are. For instance, imagine you know that two particles originally had a total of 0 momentum when they were created and became entangled. If you then measure the momentum of one of these newly quantumly entangled particles, you instantly know that the momentum of the other particle will be the exact reverse, making sure their combined total remains precisely 0. Effectively, by merely measuring one particle, you can instantly learn fundamental things about its entangled partner. This extraordinary connection works for other particle properties too, such as their position, their polarization, the orientation of their wave, or their spin, a quantum property that isn't really a physical spin. On the surface, there's nothing too weird about this. It's no different from me meeting up with a friend and discussing our plans for the evening. We agree in advance to go out, and we agree that I will pay for the evening and my friend won't. Then, no matter how far we go on our night out, or even if at some point we separate and wander off into different parts of the city, I know I will be paying, and my friend will know that he won't. This is precisely how Einstein thought it worked. He believed there must be some hidden variables, some secret prearranged information carried by the particles from the moment of their creation, which dictated their properties. This information, he reasoned, would ensure that when one particle was measured, the other would instantly display its correlating property, all without any faster-than-light communication. It was a perfectly rational, local explanation, fitting neatly into our intuitive understanding of the universe. Only it turned out that Einstein, for all his boundless genius, was wrong. Because as it happens in the quantum realm, it's not like me and my friend discussed in advance who would be paying. It's as if at the very moment I look in my wallet, the decision is instantly and simultaneously made for both of us, and my friend, no matter where he is, instantly knows his part of the deal. And the strangest part of all, we still both agree with each other. 100% of the time, no matter how far apart we are, seemingly without any prior agreement or communication. This is the truly perplexing thing about quantum entanglement and quantum physics in general. We like to think of particles as having fixed, predetermined properties, like a ball having a definite color whether you look at it or not. However, our first mind-bending experiment reveals a profound truth. Particles only truly have those properties when you detect or measure them. Until then, they're kind of vague about the whole properties thing, existing in a state of potential or cloud of possibilities, instead only relying on probabilities as defined by a mysterious quantum wave equation. This doesn't make sense intuitively, does it? Looking at a thing shouldn't be what gives it properties, right? If a tree falls in the woods, does it make a sound? According to quantum physics, not necessarily, not until an observer measures the sound waves. Let's gently delve into the first mind-bending experiment that demonstrated this profound truth, the Bell experiment, or more precisely, the Bell's inequalities test. The mathematics for this can be pretty complicated, full of arcane symbols, but bear with me, for the fundamental idea is worth the quiet journey. The experiment was first conceptualized by the aforementioned John Stuart Bell, who wanted to rigorously test Einstein's idea of hidden variables. He wanted to know definitively if particles really did carry around secret pre-existing properties that defined their attributes, or whether they truly were making some of it up on the spot at the moment of measurement, and then instantly conferring that information across vast distances. Bell noticed an interesting mathematical fact about the spin of particles. Before we go any further, I should probably mention that quantum spin isn't the same as normal physical spinning like a top or a planet. Misleadingly, quantum spin actually defines whether a particle is influenced, pushed, or pulled by a magnetic field when measured along a particular axis. The name isn't important to grasp, but it is crucial to note that these particles aren't actually physically spinning like tiny tops, and so they can have different spin values either up or down relative to the detector in almost any given direction you choose to measure them. Now let's take two quantum entangled particles, and let's imagine that we've carefully arranged it so that their spins when measured along the same axis always add up to a total of 0 between them. This means that if one particle would be pulled by a magnetic field in a certain direction, the other will be pushed by it an equal amount in the exact opposite direction along that same axis. This entanglement means that if you measure one particle's spin up along a certain direction, you know its entangled partner must be down along that same direction. This information, however, doesn't tell you anything about their spin in other perpendicular directions. One of the fascinating features of quantum spin is that if we measure an entangled particle's spin in any given direction, let's say we choose to measure it along an up and down axis, it will have a precise 50% chance to be spinning up and an equal 50% chance to be spinning down. It's like flipping a perfectly fair coin. But, and this is the magic of entanglement, once you measure the first particle, its entangled partner will then have a 100% chance to be spinning in the exact opposite direction to the first particle along the same axis. On this fact alone, there is no way to tell if the two particles already knew their spin beforehand hidden variables, or if they are somehow deciding it on the spot at the moment of measurement and then instantly conferring that decision with each other across the void. Both explanations seem to fit this simple scenario, but Bell, with his extraordinary insight, noticed a clever, profound way to distinguish between these two possibilities by asking a clever question. If you measured two quantum entangled particles from two randomly selected directions, not necessarily the same direction, what are the odds that their spin for these different directions would match, and what are the odds that they would contrast? Let's formalize this with a little simplified experiment using 3 possible measurement directions. For each particle, let's call them 1, 2, and 3, and let's define that at any time a particle's spin is measured towards a detector, its spin is up, and anytime it is measured away from a detector, its spin is down. What are the odds that both particles would be measured up, up, or down, down? when tested along randomly chosen directions? And what are the odds that they would contrast, one being up and the other down? Here we have two entangled particles, particle A and particle B, and three detectors for each capable of reading their spin in these three different distinct directions. If particle A and particle B are both read with the top detector direction 1, for example, then one of their spins will inevitably be up and the other will be down. They are entangled to be opposite along the same axis as we looked at previously. However, if particle A is read using the top detector direction 1, while particle B is read with one of the other two detectors, direction 2 or 3, these two directions of spin are not necessarily opposites in the same direct way. So particle B, in theory, has some flexibility in which way its spin goes. Quantum physics claims that the particles are fundamentally making up their attributes on the spot at the very moment of measurement. So once you'd measured the spin of particle A using the top detector, which resulted in either up or down randomly, it was predicted to be a 50-50 chance whether the spin on the other particle, particle B, when measured using one of the other detectors, would match or contrast with particle A's reading. This randomness is the key for quantum physics, as the particles aren't confined by a pre-existing opposite rule when measured along different axes. But this is not what classical physics predicted if hidden variables were at play. Let me show you what I mean very simply. Classical physics, with its intuitive view, claims that particles each carry around secret hidden information, defining their spin in any given direction from the very moment of their creation. So for our three tested directions, each particle would already have a value for its spin in that direction. They aren't making it up on the spot. They know their destiny. Let's say hypothetically that particle A's hidden information states its spin values for directions 1, 2, and 3 are up, down, up. Because particle B must always be opposite to particle A for each of these directions due to entanglement, then particle B's hidden information would automatically be down, up, down. Now let's pick out a random detector for particle A, say detector 1. Detector 1 tells us that particle A is spinning up. Now let's randomly select a detector for particle B. We select detector 1 for particle B as well. This detector gives us a reading of down. So if we measure 1 and 1, we get up and down. We can actually map out all the 9 possible combinations of detector selections. If you were to measure from 2 detectors at a given time, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. For each of these possible selections, we have fixed hidden variable results that we know already because we hypothetically defined them earlier. Of course, if you detect particles using the same detector on both particles, like 1, 1, or 2, 2, or 3, 3, you'll always get a contrasting result, 1 up, 1 down, because they're entangled to be opposite along the same axis. Both classical and quantum physics agree on this, so we're not interested in those results for testing Bell's inequality. They don't help us distinguish between the theories. So let's gently remove them from our consideration for a moment. Now let's look at the interesting combinations. What are the odds that 2 different detectors for particle A and B will see the same result, both up or both down? And what are the odds they'll differ 1 up, 1 down? Remember, quantum physics expected it to be 50-50. The particles are supposedly making up their values on the spot, influenced only by the measurement itself, and so it's perfectly random, which they'll choose when their measurement axes are different, as they aren't confined by the opposite rule in this particular setup. But in our hypothetical table, where particles have pre-existing hidden variables, classical physics says that contrasting results, 1 up, 1 down, only happen a third of the time, e.g. in combinations, like 1 or 1, 2, 2, 3, 3, in 1, where the values might be up, up, down, down, up, up. The other times, they're either both up or both down for these combinations. If we do this many, many times, assigning different random hidden variables each time, and meticulously crunched the numbers, ignoring exceptions, like where the spins of the particles are all up or down for all three directions, which simplifies the math. The important thing to take from all of this is that, according to the mathematics of classical physics, with its hidden variables, it predicts a matching outcome both up or both down 55% of the time when measured along different axes. While quantum physics continues to simply predict 50%. This seemingly small, almost imperceptible percentage difference, just 5%, was the key, the subtle hint that would unlock the universe's true nature. By quantumly entangling particles and running this test over and over again millions upon millions of times, you could now see which percentage was correct. And with astonishing precision, it turned out the winner was quantum physics. The results overwhelmingly matched the 50% prediction. Particles were indeed just apparently making up their spin results on the spot at the moment of measurement without any hidden pre-existing instructions. And this is truly spooky, because not only does that profoundly call into question our very perceptions of reality itself, is anything truly real until it's observed, but that also means that the very moment one particle decided on its spin result, its quantum entangled partner, no matter how far away, instantly knew that that decision had happened. You could test both particles at once separated by miles or even light years, and this same correlation, this instantaneous knowledge would come back. Somehow, information had traveled from one particle to the other in no time at all, far faster than light itself. So already, even without time travel, something incredibly strange was going on here. This result, achieved in countless experiments, definitively disproved Einstein's predictions about hidden variables and locality, and showed that some form of information does indeed seem to go faster than light instantaneously across vast distances. But as we hinted, we can take this profound strangeness one step further and perhaps glimpse information traveling backwards in time. There is another experiment equally ingenious and mind-bending, known as the delayed choice test. Its primary purpose was to explore the fundamental nature of light itself. Is it a wave or is it a particle? And crucially, to figure out when it decided to be one or the other. Earlier experiments, like the classic double-slit experiment, had done this in the past, to very mixed, perplexing results. Sometimes light behaved in a purely wave-like manner, creating those characteristic interference patterns on detectors that could only happen if a wave was interfering with itself, passing through multiple paths simultaneously. But sometimes, when observed, it behaved like a discrete particle hitting only a single point on a detector, as if it had chosen just one path. But most baffling of all, it seemed to change which it behaved like, depending on whether you were observing its path through space or not. If it could go through multiple paths, and no one was watching to see which it did go through, light simply went through both like a wave. But if you observed it, if you placed a detector to see which path it took, it instantly collapsed and went through just the one like a particle. This result was baffling enough, a profound mystery in itself, and certainly deserves a deeper exploration in a separate quiet video. But in 2006, a number of brilliant scientists took it one step further by asking an even more intriguing question, one that delves into the very nature of causality. What would happen if you tried to observe the light after it had already seemingly had to pick a path? Consider this elegant, simplified experiment with its profound implications. A single photon, a solitary packet of light, is sent into a beam splitter. This beam splitter is like a quantum fork in the road, with a precise 50-50 chance of either being allowed to carry on its way along path 1 or getting reflected up along path 2. Once on either path, the photon is bounced off mirrors guiding it along. Both paths then eventually reconverge at a specific point where another beam splitter is inserted. Once again, the photon arrives at this second splitter with a 50-50 chance to go either way, leading to an even chance of eventually arriving at one of two detectors placed behind it. If light were just a simple particle behaving predictably, like a tiny billiard ball sending a single photon into this experiment, would logically give you an even chance of it arriving at one detector or the other. You wouldn't be able to tell which way it went inside the apparatus, as the two beam splitters would make that impossible to know precisely. But you could certainly see where it ended up. However, this is not what occurs when the second beam splitter is present. Instead, the light produces an interference pattern at the detectors indicating, astonishingly, that the single photon went down both paths, simultaneously ultimately bumping into itself, before moving on to both detectors. This seems like strong evidence that light is a wave. It certainly behaves like one here, exploring all possibilities. But what happens if you remove the second beam splitter? Suddenly the setup changes. You do know which path the light traveled down. If light arrives at the top detector, it must have come from path 1. If it arrives at the side detector, it must have come along path 2. And something about this knowledge, this certainty of path information, profoundly spooks the light. It stops going down both paths simultaneously. Instead, each individual photon only arrives at one detector, behaving purely like a particle that has chosen a single definite path. It seems as if the act of being able to determine its path forces it to become a particle. Now here's the truly mind-bending question. The crux of the delayed choice test. What happens if you insert or remove the second beam splitter after the photon has already started its journey, after it has already entered either one or both routes? This is why the test is so aptly called delayed choice. You delay choosing how exactly you intend to detect the photon, whether by knowing which path it came down or by making that path ambiguous to you. What happens to the light? What truly happens from the perspective of our everyday understanding of causality is a very, very strange thing indeed. When this experiment was meticulously performed, it was done multiple times with the beam splitter being randomly inserted or removed by a quantum random number generator. But crucial to the experiment, it was always inserted or removed after the photon had already entered one or both paths, after it had already made its initial choice. And yet the results came back unequivocal, consistently defying our expectations. If the beam splitter was present at the end, the photon suddenly and seemingly retroactively stopped picking a single path in the past and behaved as if it had gone down, both interfering with itself. If the beam splitter was removed, the photon somehow seemed to know it would later be detected in a way that revealed its path, and so it picked a specific single path to accommodate that future observation. It was as if the future decision whether to have the beam splitter or not changed what the photon did in the past. So what truly is happening here? Is it really true that particles somehow saw the future? Did the experiment cause information to be sent back into the past? Or is there some other profound principle at play here? One that explains this whole thing, that accounts for the instant transmission of information between quantum entangled particles and allows it to be perfectly rational that light could travel down one path or both at the same time. Personally, I'm inclined to think that the latter is more likely. We clearly don't fully understand what is happening here. Our models are incomplete, but it must be admitted if we don't understand what is happening, there's nothing rigorously speaking to say that causality isn't being ignored in some subtle, profound way at the quantum level. Maybe on the quantum level time really is more fluid, more flexible, more interconnected than it is up here in the larger macroscopic universe. Perhaps space and time as we perceive them simply do not apply in the same rigid way down there in the realm of the truly tiny and ephemeral. And maybe one day someone will be able to come up with a unifying theory, a brilliant new framework that allows all these strange, baffling phenomena to finally make perfect, elegant sense, weaving them into a coherent tapestry. Until then, we'll just have to keep asking the same profound, unsettling question: can information travel backwards in time? Until then, we'll just have to all agree on one thing. Quantum physics is exquisitely strange. It is a testament to the universe's boundless capacity for mystery. A constant reminder that reality is far richer and more complex than our everyday senses can ever convey. Thanks for joining me on this quiet, mind-bending journey. I was honestly blown away by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community of curious minds. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. May your thoughts be gentle and your dreams be filled with cosmic wonder.